the metal that powers the planet. Every second, 3 electric cars are sold worldwide. Every hour, 50,000 smartphones roll off production lines, and all of them depend on one element: lithium, the white gold of the 21st century. The lightest metal on Earth, which you'll never see in its pure form because it instantly explodes on contact with water. But it's what fires up your phone, drives electric vehicles, and will power humanity's future. How do salt lakes high in the Andes transform into an energy source for billions of devices? You'll discover why lithium is called white gold, how giant evaporation pools the size of a city work, and why a real geopolitical war has erupted over this metal. Watch until the end. The finale will reveal what's behind every percentage point of your smartphone's battery. This is the story of a metal that changed the world in just 20 years.
Lithium's story began in 1817 on a tiny Swedish island called Uto. A young chemist, Johann August Arfwedson, was analyzing a rare mineral called petalite when he discovered something strange. This was a metal, but incredibly light, lighter than water. Arfwedson named it lithium from the Greek word lithos, stone. Ironic, right? A stone that floats. In 1821, British chemist William Brand first isolated pure metallic lithium through electrolysis of molten salt. What he saw blew his mind. A silvery white metal so soft you could slice it with a knife like butter, and so light that a chunk of lithium actually floats on water. But that contact with water, it lasts maybe a second. Lithium instantly explodes into a violent reaction, hissing, smoking, and it can catch fire. For 150 years, lithium was just a lab curiosity. They used it in medicine to treat mental disorders, in glass and ceramic production. But everything changed in the 90s.
In 1991, Sony released the first commercial lithium-ion battery. It was a breakthrough. Before that, batteries were heavy, short-lived, drained fast. Lithium-ion batteries turned out to be 3 times lighter and held their charge way longer. The portable electronics revolution began. Cell phones became compact, laptops became light, cameras became long-lasting. But the real explosion in demand happened in the 2010s when electric vehicles hit the market. Tesla, Nissan, BMW all built their cars on lithium-ion batteries. One electric vehicle requires 130 to 175 pounds of lithium. For comparison, a smartphone contains just 1/10 of an ounce. Demand for lithium jumped from 30,000 tons in 2010 to 550,000 tons in 2023, and that's just the beginning. Forecasts predict 3 million tons by 2030. Lithium transformed from a rare lab element into a strategic resource more important than oil.
But where do you get that much lithium? On Earth, lithium isn't rare. It's the 33rd most abundant element. But here's the thing. Concentrated deposits, not so common. There are 2 main sources, hard rock and salt brines. Hard rock means spodumene, a rare mineral mined in Australia, Canada, Zimbabwe. But the future? It's in the brines. High up in the salt lakes of South America, at 10 to 13,000 feet above sea level, lie the planet's largest lithium reserves. It's called the Lithium Triangle: Bolivia, Chile, and Argentina. Bolivia's Salar de Uyuni is the biggest salt flat on Earth. 4,000 square miles of blinding white salt under an endless sky. Looks like a massive frozen lake. Beneath that salt crust, brine, containing about 9 million tons of lithium. That's half the world's reserves. Chile's Atacama, the driest desert on the planet. Here too, massive lithium deposits hide in underground brines.
Now, let's break down how lithium is actually extracted from these salt lakes. The process looks almost magical. First,
They drill wells anywhere from 65 to 330 feet deep. Powerful pumps suck up brine from these wells, a salty liquid similar to seawater, but way more concentrated. A single liter of this brine contains anywhere from 300 to 1,500 milligrams of lithium. For comparison, seawater has just 0.17 milligrams per liter. The pumped brine gets channeled into massive evaporation ponds. Picture this: artificial lakes covering dozens of hectares. From above, they look like giant colored squares: blue, turquoise, green, yellow. The color depends on mineral concentration and microorganisms. These ponds are arranged in a cascade, like giant steps. The brine flows from one pond to the next, and at each step, the magic of evaporation happens.
Under the scorching sun of the high-altitude desert and relentless winds, the water evaporates, slowly, month after month. The Atacama receives less than a millimeter of rainfall per year, but the sun shines 300 days a year, perfect conditions for evaporation. The lithium concentration in the brine gradually increases. First, unwanted salts precipitate out of the solution: sodium chloride, sulfates. They're collected and removed. The process takes 12 to 18 months. Yeah, you heard that right. Over a year just waiting for the sun to do its work. During this time, the lithium concentration grows by roughly 20 times. What started as a weak brine transforms into a thick, oily solution containing about 6% lithium. The brine turns amber yellow, almost like honey. It's pumped into specialized tanks and shipped to a chemical plant. Here begins the final stage of transforming salt water into white gold.
At the plant, concentrated brine is treated with sodium carbonate, basically baking soda. A chemical reaction happens and a white precipitate crashes out of solution: lithium carbonate. It's not the metal yet, but it's a crucial compound. The precipitate gets filtered, washed, dried. What you end up with are fine white crystals, like powdered sugar. That's why lithium's called white gold. It actually is white. Lithium carbonate gets bagged up and shipped all over the world. Most of it goes to China, Japan, South Korea, wherever batteries are made. But that's not the end of the road. To make batteries, you need lithium hydroxide. Lithium carbonate gets dissolved in water, treated with calcium hydroxide. You get a solution of lithium hydroxide, which then gets evaporated. What remains are white crystals of lithium hydroxide, the final product, ready for manufacturing battery cathodes. The whole cycle, from pumping brine to getting the finished product, takes about 2 years.
There's another method for extracting lithium, from hard rock deposits. In Australia and China, they mine spodumene, a mineral that contains lithium. They blast the rock, crush it, grind it into dust. Then they heat it to 1900 degrees Fahrenheit in massive rotating kilns. At that temperature, the spodumene changes its structure, becomes more reactive. The roasted rock gets mixed with sulfuric acid. A violent reaction kicks off, releasing heat and toxic gases. The lithium moves into a lithium sulfate solution. This solution gets purified of impurities, treated with sodium carbonate. Lithium carbonate precipitates out, the same product as from the brines. But this method is way more energy intensive and expensive. You need high temperatures, massive volumes of chemicals, tons of waste gets generated. That's why the future belongs to brines. Even though right now about 60% of the world's lithium comes from hard rock, the balance is gradually shifting towards salt lakes.
Now let's look at where all this extracted lithium goes. 75% of global production goes into batteries. A lithium-ion battery is a complex device. Inside are 2 electrodes, a cathode made of lithium oxide with cobalt or manganese, and an anode made of graphite. Between them is an electrolyte containing lithium salts.
During charging, lithium ions move from the cathode to the anode and slide between the graphite layers. During discharge, they move back, and this flow creates an electrical current. Brilliant simplicity. Lithium is ideal for this because it's the lightest metal capable of giving up electrons. A single lithium atom weighs just 7 atomic units. For comparison, lead weighs 207. That's why lithium batteries are so light and energy-dense. A modern Tesla Model 3 electric vehicle contains about 24 pounds of pure lithium in its 1,060-pound battery. This battery can travel over 300 miles on a single charge.
Beyond batteries, lithium is used in ceramics and glass production. It lowers melting temperatures and makes materials stronger. In metallurgy, lithium gets added to aluminum alloys, makes them lighter and tougher. In nuclear power, lithium produces tritium. In medicine, lithium carbonate is still used to treat bipolar disorder, stabilizes mood. Global lithium production in 2023 hit around 130,000 tons of pure metal equivalent. The major producers, Australia, 40%, Chile, 25%, China, 14%. Lithium prices rocketed from $5,000 per ton in 2020 to $80,000 in 2022, then crashed to $30,000. The market's volatile because demand is growing faster than supply. A real geopolitical battle has erupted over lithium. China's buying up deposits worldwide. The US is trying to build its own supply chain. Europe's hunting for alternative sources.
And just like that, having journeyed from salt lakes high in the Andes through 18 months of evaporation under the merciless desert sun, through chemical plants and the most complex purification processes, lithium emerges into the world, the white gold of the 21st century, the lightest metal that powers modern civilization. This is the story of how humanity learned to turn saltwater from ancient lakes into energy for billions of devices. Every time you charge your smartphone, get into an electric vehicle, or fire up your laptop, remember, inside beats a heart made of lithium, the metal for which we mine deserts and drain salt flats. The metal behind the energy revolution and the move away from oil. The metal without which the future of humanity is unimaginable. White gold extracted from snow-white salt lakes to power the planet with the energy of tomorrow. Lithium isn't just an element on the periodic table. It's the key to a future that's already here.
Every year, over 150 million cubic meters of plywood are produced worldwide, enough to have a train of wagons loaded with these sheets circle the Earth at the equator several times. But how is an ordinary tree trunk turned into this unique material, used in furniture, construction, and even shipbuilding? What secrets does the process hide? Starting with spa treatments for logs and ending with a hot press where layers of wood are permanently bonded into a monolith. Watch until the end and you'll learn about the secret pencil that remains after production and why it too has its own value.
It all starts in the forest, where the best specimens are selected for plywood production. You need perfectly straight, cylindrical trunks without a large number of knots or defects, preferably from birch, alder, or pine. After delivery to the factory, the logs undergo the first and very important stage of preparation, hydrothermal treatment. They are submerged in giant pools of hot water, where they spend several hours and sometimes a whole day. This kind of spa for logs has a purely practical purpose. The hot water softens the wood, making it more plastic and pliable. Without this, further processing would be impossible. After the bath, the logs are fed to a line where their bark is stripped off. Special machines quickly and efficiently clean the trunk, leaving a smooth, light surface.
The heart of the entire plywood production process is the peeling lathe. This is where something incredible happens. The prepared log, clamped at both ends, begins to rotate at a huge speed around its axis. A long, razor-sharp knife is slowly brought towards it. As it cuts into the wood, it begins to peel off not shavings, but a continuous, seamless ribbon just 1 or 2 millimeters thick. It's like unrolling a giant roll of paper towels. The machine literally unrolls the trunk like a scroll of ancient papyrus, turning a 3-dimensional cylinder into a flat, long ribbon. This ribbon is called veneer. The long sheet of veneer moves further down the conveyor, where giant clippers chop it into sheets of standard size. All that's left of the log is a thin central cylinder, the so-called pencil, which is then used for other purposes. Freshly made veneer contains a lot of moisture, which is an enemy of the strength of the future plywood. Therefore, the next mandatory stage is drying. The veneer sheets are fed into long, multi-tiered drying chambers. Inside them, as if on the shelves of a giant cabinet, the sheets slowly move on a conveyor while hot air intensely blows on them from all sides. In a few minutes, the damp and flexible sheets turn into light, slightly brittle, and perfectly dry blanks.
At this stage, the dried veneer sheets are sorted by quality. Then they pass through a glue spreading machine. Special rollers, dipped in a bath of synthetic glue, apply a uniform, sticky film to one side of every other sheet. Next begins the process of forming the layup. A dry sheet of veneer is placed on a table, and on top of it, a sheet coated with glue. And here lies the main secret. Each subsequent sheet is laid so that the direction of its grain is perpendicular to the previous one. If the first sheet's grain runs lengthwise, then the second's runs crosswise, and the third's lengthwise again. This cross-grain structure is the key to plywood's strength. It paralyzes the wood's natural tendency to split and evenly distributes the load.
That's why plywood is equally strong in all directions. The number of layers in the layup is always odd, so that the structure is symmetrical. The formed layups of veneer are fed to the most powerful section of production, the hot press. This is a giant multi-story structure, between whose plates several dozen future plywood sheets are loaded simultaneously. With an enormous force reaching tens of kilograms per square centimeter, the plates compress the veneer layups. At the same time, the plates are heated to a temperature of 150 degrees Celsius. Under the influence of high pressure and temperature, the glue polymerizes, permanently bonding the layers into a single, incredibly strong monolith.
Hot sheets of plywood come out from under the press and are stacked for gradual cooling. After this, they undergo final processing. Powerful circular saws trim the edges, giving the sheets precise geometric dimensions. Then comes sanding. The sheets pass through sanding machines with endless abrasive belts, which make their surface perfectly smooth. After this, each sheet undergoes strict quality control. Inspectors check it for defects, delaminations, knots, or glue spots. Depending on the surface quality, the plywood is assigned a certain grade, and a marking is applied to it. The finished stacks of plywood are sent to the warehouse, to later become part of furniture, houses, and ships. The pencil that remains after peeling the veneer is a vivid example of how modern production strives for maximum waste-free efficiency. It is not waste, but a valuable raw material. If the cylinder is massive enough, it is sent to a sawing line, where it gets a second life in the form of lumber. Small boards and bars are cut from it, which are ideal for creating the invisible but strong frames for sofas and armchairs, legs for chairs, elements of children's beds, or wooden pallets.
Steel cables were invented to replace ropes made from natural fibers. Ropes couldn't handle heavy loads. Chains were stronger but 10 times heavier. Steel cables solved both problems. Today, these cables hold up bridges, lift cranes, anchor oil platforms at depths of over half a mile. Diameter up to 21 inches. Weight 70 tons. Braking strength 9,700 tons. That's the weight of 50,000 cars. How do you make a cable that won't break? Today you'll see the complete process, from a steel rod just 1/5 of an inch in diameter to a giant cable 900 feet long. If you want to see how thin wire transforms into a monster with a 10,000-ton braking strength, subscribe to the channel. Here we show you the industries that hold the world together. History. The modern steel cable was invented in 1834 by German engineer Wilhelm Albert. He developed it for coal mines. Hemp and manila grass ropes couldn't handle the job. The weight of coal in a cage? Over 3,000 pounds. Mine depth? Nearly 1,000 feet. Hemp rope broke from moisture and rubbing against shaft walls. Albert braided cable from steel wire. Wire diameter, just under 1/10 of an inch. 6 wires per strand. 6 strands around a core. Cable diameter, 3/4 of an inch. Strength, 5 times stronger than hemp. Lasted years instead of months. During the World War, steel cables anchored mines to the ocean floor. Deployment depth, up to 300 feet. Water pressure, 150 pounds per square inch. A cable just over an inch thick held a 600-pound mine, plus current and waves. Today, steel cables are everywhere. Cranes, elevators, suspension bridges, drilling rigs, ski lifts. Wire drawing, it all starts with rod, a steel wire 5.5 millimeters in diameter. The rod is made from grade 70 to 80 steel. Carbon content, 0.7 to 0.8%. Manganese, 0.6%. This is high carbon steel, hard and strong. The rod unwinds from a coil weighing 2 tons. It's pulled through a drawing mill. This is a series of dies with holes of decreasing diameter. First die, diameter 4.8 millimeters. Second, 4.4. Third, 4.0. Fourth, 3.6. Fifth, 3.2. Sixth, 2.8. Seventh, 2.4. Eighth, 2 millimeters. 8 passes total. Each pass reduces the diameter by 10 to 15%. Between the dies are pulling drums. Drum diameter, 500 millimeters. Rotation speed, 300 revolutions per minute. Linear drawing speed, 470 meters per minute. That's 28 kilometers per hour. The wire heats up from friction. Temperature exiting the die, 200 degrees Celsius. Cooled with water. After drawing, the wire is hard. Tensile strength, 1,800 megapascals. Elongation, 2%. It's brittle. Heat treatment needed. Heat treatment. Heat treatment. The wire gets heated in a furnace to 1,650 degrees Fahrenheit. Hold it there for 20 minutes. The steel structure reorganizes. Carbon dissolves into the lattice. Then it cools in air at a rate of 180 degrees per hour. Slow cooling. You get tempered steel. Hardness drops, but ductility increases. Elongation, 8%. The wire's now flexible, ready for rope making. Strand twisting. Take 6 wires, diameter 0.08 inches. Twist them around a central 7th wire. Lay length, 4 3/4 inches. That's the distance one wire takes to complete one full wrap around the center. Helix angle, 15 degrees to the axis. Twist direction, right hand. Looking along the strand, the wires spiral clockwise. You get a strand, diameter 0.24 inches. Starting wire length, 3,300 feet. Finished strand length, 3,100 feet. The difference, that's what the twisting eats up. The strand bends easy. Bend radius, 6 inches. Strand strength, 70% of the combined wire strength. Losses from bending and friction. Rope stranding. 6 strands, 1/4 inch in diameter, twisted around a core. The core is organic. A hemp rope, 1/4 inch diameter. It's soaked in lubricant. Hemp is elastic. It absorbs shock loads. Stores lubricant inside the rope. There can be more strands. Standard construction is 6 by 7. 6 strands with 7 wires each. There are 18 by 7 ropes. 18 strands, 7 wires per strand. There's 36 by 7. More wires mean a more flexible rope. The diameter of a 6 by 7 rope with core 1/4 inch wires is about 3/4 of an inch. Breaking strength is 50 kilonewtons. That's 5 tons. Weight is about half a pound per foot. The rope gets wound onto a drum 6.5 feet across, 5 kilometers per drum. That's over 3 miles. Weight of the drum with rope is 8 tons. The ropes ship out to plants that make giant cables. Manufacturing giant ropes. United Offshore Services in the Netherlands makes ropes ranging from 4 3/4 inches to 21 inches in diameter. The factory houses a machine that's over 650 feet long. It twists finished ropes around a central core rope. Here's an example. They're making a rope that's 13 inches in diameter. They take 6 ropes, each about 4 inches thick, plus a central rope that's 4 3/4 inches. Then they twist them together. The rope spools get mounted on a rotating carousel. The carousel is nearly 40 feet across. It spins at 2 revolutions per minute. The ropes unwind from the spools. They pass through guide rollers. They twist around the central rope. The lay length is 71 inches. The lay angle is 20 degrees. Twisting speed is 11.5 feet per minute. In 1 hour, they produce 690 feet of rope. The finished 13-inch rope gets wound onto a spool that's 13 feet in diameter. Breaking strength? 9,700 tons. That means this rope won't snap until you load it with 9,700 tons. Marking and lubrication. The cable gets marked along its entire length with different colored paints. Red section, the start. Yellow, the middle. Blue, the end. Every 33 feet, a marker with a number. Then they lubricate it. They use lithium-based grease. Drop point temperature, 356 degrees Fahrenheit. The grease protects against corrosion and reduces friction between the wires. The cable runs through a bath of liquid grease heated to 176 degrees. The grease soaks into the core and between the strands. Then they apply an outer layer, anti-corrosion coating. It's a thick paste made from paraffin and corrosion inhibitors. Coating thickness, 0.02 inches. The final cable, length 558 feet, diameter 13 inches, weight 76 tons, breaking strength 10,700 tons. They move it with a crane rated for 165 tons. One end gets hooked. They lift. The cable hangs vertically. Lift height, 164 feet. You need a tower. At the factory, there's a tower 197 feet tall, specifically for this. super long ropes. Hendrik Vader Group in the Netherlands makes the longest ropes in the world. Length, 920 feet. Diameter, 16 inches. Different technology. The machine travels along rails 1,000 feet long. At the start sit spools of rope, 8 spools. On each, a rope diameter 10 inches, length 920 feet, weight 110,000 pounds. Strength of each, 7,700,000 pounds. The machine starts moving. Speed, 6.5 feet per minute. The ropes unspool. They twist around a central rope diameter 10.25 inches. Lay length, 6.5 feet. The machine travels 1,000 feet in 2.5 hours. You get a rope diameter 16 inches, length 920 feet, weight 440,000 pounds. Strength, 31 million pounds. That's the weight of 80 tanks. At the end, they make a loop. They bend the rope back 15 feet. They splice the free end with the main rope. You get a loop 15 feet long. Loop diameter, 5 feet. The splice is locked with steel clamps. 10 clamps. Each clamp, 2 steel half cylinders. Tightened with 8 M36 bolts. Torque, 590 foot-pounds. Transport and deployment. A rope 900 feet long, weighing 440,000 pounds, lies coiled on the factory floor like a snake. It needs to be loaded onto a ship. They use 3 forklifts, each rated for 55,000 pounds. They lift the rope at 3 points. Drive it to the dock. Distance 1,600 feet. Speed, half a mile per hour. Time, 30 minutes. At the dock stands a crane rated for 880,000 pounds. It grabs the rope by its loop, lifts it, lowers it into the ship's hold. The ship carries the rope to Norway, to the Åsgard oil and gas field in the North Sea. Sea depth, 980 feet. A floating production platform sits there. Platform weight, 110 million pounds. The platform is held by 8 anchors. One rope 16 inches in diameter runs to each anchor. Each anchor weighs 440,000 pounds. Sits on the seabed. The rope runs from the anchor to the platform. Rope tension, 2 million pounds in calm weather. In a storm, 6.5 million pounds. Safety factor, 5 times. The rope is rated for 20 years of service. Inspected every 3 months. They send down an underwater vehicle with a camera. Inspect every foot. Looking for broken wires, corrosion, wear. If wear exceeds 10%, they replace the rope.
Have you ever seen what molten bronze looks like? I have. It's golden, almost like the sun, and flows slower than water, thick, heavy, with this inner weightiness to it. And when 70 tons of this metal get poured into a single mold all at once, it's a sight you can't look away from. Today we're at a factory that makes propellers for military ships. This is one of those places they don't run tours through and almost never film inside. And I'm going to show you the entire journey from molten bronze to a polished giant that will silently push thousands of tons of steel through the ocean. Let's start with a question I asked myself when I got here. Why bronze? A warship is a steel machine. Steel hull, steel superstructure, steel weapons. So why make the propeller from a different material? The answer is simple yet profound. Steel rusts in seawater. The propeller is constantly submerged, constantly spinning, constantly in contact with an aggressive environment. A steel propeller would turn into a rusty hedgehog in just a few years, one that can't do its job anymore. That's why they use nickel aluminum bronze here, an alloy that sailors and metallurgists call nibral for short. Nibral is a mix of copper, aluminum, nickel, and iron in precisely calibrated proportions. Copper provides the base and corrosion resistance. Aluminum strengthens the alloy and reduces weight. Nickel adds hardness and erosion resistance, and iron refines the grain structure, making the metal uniform. Every element here is deliberate, the result of decades of research and real-world testing. Nibral doesn't rust, resists erosion incredibly well, and has enough strength to handle the loads from spinning at full speed underwater. Now, about scale. A propeller for a destroyer or nuclear submarine, this isn't something you can pick up with your hands. The diameter of such a propeller reaches 20 feet or more, and each blade is comparable in size to a small car. The weight of the finished product, dozens of tons. And it all starts with 70 tons of liquid bronze that needs to be poured into a single mold in one continuous process. 70 tons. That's roughly the weight of 12 fully loaded pickup trucks. And all this massive metal at a temperature of around 2,000 degrees Fahrenheit has to get into the mold evenly, no pauses, no stops. The metal is melted in large induction or arc furnaces. Depending on the plant's configuration, there might be several of these furnaces, and they run in parallel to accumulate the necessary volume of molten metal by the time of pouring. When the metal hits the right temperature, lab techs take a sample, a small portion of the melt, and send it for rapid chemical analysis. If the element ratios check out, they greenlight the pour. If something's off, they adjust it right there in the furnace, adding whatever element is needed, then take another sample. The pour happens from a big ladle suspended from an overhead crane. They tilt the ladle, and metal starts flowing into the gating system of the mold. It looks like this, a thick golden stream with bright glow and a cloud of steam rising up. The air shimmers from the heat, and 30 feet away you can feel the hot wave hit your face. The foundry workers stand off to the side in protective suits and shields. Even several yards out, the heat hits your whole body. They control pour temperature by adjusting the ladle tilt. Too fast and the metal churns turbulently in the mold, trapping air and creating voids. Too slow and the first portion starts solidifying before the mold fills, leaving internal seams in the casting. So the pace stays steady, continuous, dialed in by experience. When the mold is complete, they leave what's called a riser at the top, an extra reservoir of metal that feeds the casting as it shrinks during cooling. Without it, shrinkage cavities form inside the propeller, voids that would render the blade useless. The riser gets cut off later, but during the pour, it's a critical part of the process. The mold for a propeller is a massive structure that takes up a significant portion of the foundry floor. It's assembled over weeks from special molding sand reinforced with binding resins. Each blade has its own complex geometry, twisted, uneven, with a precisely calculated profile. This geometry is built into the sand mold with high precision. The raw casting already needs to be very close to the final part. Worth noting separately are the cores. Cavities are designed inside the blades to reduce weight without sacrificing strength. To form them, sand cores are mounted in the mold on metal supports called chaplets. During the pour, the chaplets fuse with the base metal and become part of it, while the cores are later knocked out of the finished casting. Sounds simple, but in practice, it's precision work, carefully controlling the position of every rod. If a rod shifts under the weight of molten metal during the pour, the blade wall comes out uneven. An uneven wall means imbalance. Imbalance on a submarine propeller means vibration. Vibration means noise. And noise underwater? That's a death sentence for a sub, because enemy hydrophones will pick it up. This brings us to the main theme of this facility: silence. A warship, and especially a submarine, must be as quiet as possible. The propeller is the primary source of underwater noise. There are two mechanisms: mechanical noise from imbalance and vibration, and cavitation noise. Cavitation is a phenomenon where microscopic vapor bubbles form on the blade surface due to pressure differences, then collapse with a distinctive crackle. Each pop is a micro-impact that, over time, destroys even bronze, leaving small pits on the surface. But the main problem isn't wear, it's sound. That crackling travels brilliantly through water and is easily detected by sonar systems. That's why blade surfaces must be perfect. No roughness, no waviness, no deviations from the calculated profile. That's exactly why there's a 5-axis CNC milling machine standing here. If you've never seen one of these machines, picture something between an industrial robot and a building. The work envelope can handle parts up to 20 feet in diameter. The spindle and cutter move simultaneously along 5 axes, 3 linear and 2 rotational. This lets the tool approach any point on a complexly twisted blade at exactly the right angle and remove metal with micron-level precision. The price tag on one of these machines? A small fortune. But without it, achieving the required surface quality on parts this size is simply impossible. Machining a single propeller takes several weeks. Weeks, not hours. The machine strips away chips continuously, layer by layer, closing in on the final profile. Bronze shavings curl into golden spirals and drop into the catch pan, while beneath the cutter emerges a surface smooth as glass. Operators regularly pause the process to measure blade geometry using specialized probes and laser scanners. Any deviation from the theoretical profile? The program gets adjusted. The goal is to achieve a surface that matches the blueprint to within hundredths of a millimeter on a part that's 20 feet across. That's like drawing a perfect room-sized circle without deviating from the line by more than the thickness of a sheet of paper. After machining comes balancing. The propeller gets mounted on a balancing stand and spun. Sensors detect exactly where the imbalance is and how much. Technicians manually remove metal from specific spots, literally just a few grams at a time, until the propeller reaches the required balance level. The process is painstaking. Shave off a tiny bit, measure. Shave again, measure again. Over and over until the sensors show it's within spec. On a civilian ship, this level of precision would be considered excellent. On a military vessel, it's the minimum acceptable standard. The final inspection includes complete measurement of every blade, surface roughness checks, and verification of the metal's chemical composition using samples taken during the melt. Each propeller gets a full documentation package, from the melt's chemical analysis to balancing protocols and laser surface scanning reports. This isn't just paperwork. It's a legal and technical passport for a product that'll go on a warship and serve for decades under the harshest operating conditions. I stood next to a finished propeller before shipping, trying to wrap my head around the fact that I was looking at something that had gone from liquid bronze to this golden, polished giant in just a few months, through the work of dozens of people and one very large machine. Somewhere out in the ocean, this propeller will spin in complete darkness, pushing thousands of tons of steel forward. And it'll do it silently. Because that's exactly what it was built to do.
In the scorched Arizona desert, among endless sands, lies the most expensive graveyard on the planet. 4,000 aircraft, worth over $35 billion. This isn't a museum and it's not a junkyard. This is where war machines that once ruled the skies come to die. Picture this: an area bigger than 2,000 football fields, and on every square foot, stories of wars, victories, and defeats. Legendary B-52s that bombed Vietnam rest here. F-14S that defended the skies over Iraq stand here. New patients arrive every single day. But what happens to these giants after they touch down for the last time? Some get stripped for parts in a matter of weeks. Others sleep here for decades, waiting for resurrection. And some just get wiped off the face of the earth. Stick around till the end. You'll find out how machines worth millions die and why this place is called America's Boneyard. (1946). World War II had just ended, and America faced a problem nobody had thought about. Tens of thousands of warplanes were suddenly obsolete. B-17Es, B-24Es, fighters, bombers, all worth billions. But the world wasn't at war anymore. Selling them was out of the question. The technology was classified. Keeping them on active bases? Too expensive. So the military found a solution. Davis-Monthan Air Force Base in Arizona, a place where it rains 4 times a year, where humidity is practically zero, and where the temperature kills any corrosion. Hard-packed alkaline soil, natural concrete, no need for hangars or runways. The desert climate turned this place into the perfect graveyard for aircraft. The first 600 planes from the war flew in. They were parked in neat rows, mothballed and forgotten. Nobody imagined that 70 years later, there'd be over 4,000 aircraft sitting here. The 60s, the Cold War is at its peak. America is building bombers capable of delivering nuclear weapons to Moscow. The B-52 Stratofortress. Weight, 83 tons. Wingspan, 184 feet. A machine built to destroy cities. By the 70s, they'd built over 700 of them. But technology changes fast. Missiles appear that fly faster and more accurately. Bombers become obsolete. Where do you put these giants? Davis-Monthan. The base is expanding. Now it's not just a storage yard, it's a whole industry. 365 personnel. Mechanics, engineers, preservation specialists. They take in aircraft, assess their condition, and decide the fate of each plane. Some get preserved for long-term storage. Others get stripped for parts within a month. Still others head to the guillotine, a giant machine that slices the fuselage into pieces. The decision comes down to one thing. Does the military need this model? The 90s. The Cold War is over, and at the airplane graveyard, the largest destruction in aviation history begins. The Strategic Arms Reduction Treaty demands proof. Bombers must be destroyed so Russian satellites can see it from orbit. They position a B-52 on the pad, and a 13-ton guillotine drops onto the fuselage. The crunch of metal echoes for half a mile. In 15 minutes, a machine that cost $100 million becomes chunks of aluminum. Cameras capture everything for the satellites, proof of destruction. Over several years, they cut up 365 B-52s this way. Each aircraft is a story. Vietnam, Operation Desert Storm, dozens of combat missions. But treaties matter more than history. The metal goes to the smelter. One bomber yields about 50 tons of aluminum, enough to make 1,200 bicycles. That's how Legends of the Sky die. The process begins long before the aircraft touches down in Arizona. The military makes the call. This bird is retired. Could be a lot of reasons. Outdated model, maintenance costs through the roof, political decisions, structural wear after thousands of flight hours. The plane makes its final flight. Pilots joke it's the last ride to paradise. Though for the machine, it's more like a waiting hell. Davis-Monthan Base greets it in the receiving area. First thing, complete inspection. Engineers check every system. Engines, avionics, hydraulics, electronics. A detailed report gets compiled. This will determine the aircraft's fate. Category 1. Storage with restoration potential. These birds can return to service in 5, 10, even 15 years. Category 2, an organ donor. Everything valuable gets stripped out. Category 3, my complete disposal. This plane goes under the cutting torch within weeks. Decision made. Preservation begins. If a plane ends up in storage, it's prepped for a long sleep in the desert. This isn't just park it and forget it. It's a meticulous process refined over decades. First, they drain all fluids. Fuel, hydraulics, oils, every last drop. Even the slightest residue can cause corrosion or fire. Then they preserve the engines. They're coated with a special compound that protects the metal from oxidation. The cockpit is sealed. Every opening, air intakes, nozzles, hatches, gets covered with special film. It reflects sunlight and keeps the internal temperature from reaching critical levels. Without it, the cockpit turns into an oven. Desert temperatures in summer hit 120 degrees Fahrenheit. Electronics are sealed in protective bags with silica gel, which absorbs moisture. Landing gear gets treated with anti-corrosion coating. The whole process takes about 3 weeks. After that, the plane is rolled out to its spot. Neat rows like a parade of frozen giants. Here it can sit for years. But most aircraft meet a different fate. They become donors. Picture this. Hundreds of planes flying overhead that need parts. An engine for an F-16 costs $3 million. Brand new. But what if you pull it from a mothballed airframe? $800,000. The savings are massive. That's why there's an entire disassembly industry here. Mechanics show up with orders. Need a radar? Pull it from tail number 412. Need a turbine? That F-15 over there will give up its own. The process is surgical. Aircraft aren't stripped barbarically. They're disassembled by the book. Every part gets cleaned, inspected, tested. They document serial numbers, flight hours, condition. Then they package it and ship it to warehouses. One retired aircraft can give life to dozens still flying. Every year, more than 20,000 parts ship out from here. The value of those parts? Over $500 million annually. The aircraft boneyard operates like a giant parts store for all of American aviation. But some planes aren't so lucky. Their time is truly up. The model's obsolete and nobody needs their parts. Or treaties demand complete destruction. That's when the final act begins. The aircraft gets rolled onto a special pad. This is where the monster works, the Igor guillotine. 13 tons heavy, tall as a 3-story building. It's a hydraulic cutter that can slice a B-52 fuselage clean in half in 20 seconds. Brutal process, but efficient. The blade drops and metal 3/4 of an inch thick cracks like cardboard. The fuselage splits apart. Then excavators with shears roll in. They cut the wings, rip off the tail, crush the cockpit. In one day, a single crew can turn 5 aircraft into a pile of scrap. Aluminum gets sorted by grade, titanium separate, steel separate. All of it goes to the smelter. One F-14 Tomcat yields about 12 tons of metal, enough to make 40,000 soda cans. Circle of materials. But not every plane stays here forever. Some come back to life. History's seen dozens of cases where an aircraft that slept 10 years in the desert took to the skies again. The most famous example? B-1 Lancers. In 2004, they were pulled from service and mothballed. 5 years later, the military realized they'd made a mistake. These machines were still needed. 18 airframes were brought back online. The restoration process took months. Engineers stripped protective coatings, checked every system, replaced all fluids, tested engines. Cost of restoration? $15 million per airframe? That's 10 times cheaper than building new. These B-1s flew combat missions again. Afghanistan, Syria, Iraq. Machines considered dead were dealing death once more. The Arizona desert proved to be better storage than any hangar. Dry air preserved the metal perfectly. Not a speck of rust after 10 years under open sky. 4,200 aircraft sit at the boneyard today. That's more than all the aviation museums in the world combined. This collection's worth over $35 billion. Around 300 new birds arrive every year, and roughly the same number leave. Some for parts, some for the smelter, some return to active duty. The base operates year-round, 365 days. No days off. A staff of 400 keeps this giant machinery of death and resurrection running. The economic impact is massive. Annual savings for the U.S. Air Force, over $1 billion. Money they don't have to spend on new parts. Foreign militaries come here like it's a marketplace. They buy whole aircraft for their museums or training. Australia bought 20 retired F-18 Hornets. Israel took several dozen helicopters. The boneyards become an international hub for trading aviation history. And so, beneath the scorching Arizona sun, ends the life of machines that once embodied power and technology. Each of these aircraft isn't just metal and electronics. These are the stories of pilots who trusted them with their lives. These are missions flown over Vietnam, Iraq, Afghanistan. These are technologies humanity spent decades developing and billions of dollars perfecting. There's no museum romance here. Here's the harsh truth. Every machine is mortal, even those that ruled the sky. But there's a certain justice in this. Aircraft don't rot in junkyards. They donate their organs to brothers still flying. They transform into materials for new technologies. Some resurrect for final combat missions. The aircraft boneyard isn't the end, it's transformation. From the ashes of old machines, new ones are born. And every time a fighter climbs into the sky with an engine stripped from a mothballed bird, somewhere in the desert a metal giant smirks. I'm still flying, just differently.
A plane that looks like a whale flies through European skies. It doesn't carry passengers, it carries other planes. Wings 100 feet long, fuselage sections as tall as a house. This is the Airbus Beluga XL, Europe's biggest cargo plane. 112 tons of freight, a cargo hold 29 feet across. Inside, it can fit 2 Airbus A350 wings at once. Without the Beluga, Airbus production would stop in a week. Today, we'll see how this giant is born, from an aluminum sheet to the first roar of its turbines. The Beluga XL is a puzzle made from parts created at 5 points across Europe. The base, an Airbus A330. Its lower fuselage, wings, and landing gear are assembled in Toulouse. But the nose section? That's made by Stelia at their plant in Mayotte, France. 40 feet long, 18 tons. Inside, the cockpit, avionics, hydraulics. All on a plug-and-fly principle. Panels from aluminum alloy 2024 with copper and magnesium are formed on presses capable of 1,300 tons of force. The frame is assembled from bulkheads and stringers, then the skin is riveted on top. 12,000 rivets, each about 1/6 of an inch in diameter for a single nose. The upper expanded fuselage, the heart of the Beluga, is produced by Premium Aerotech and Dehard. 3 sections, 2 side panels and a roof. 29 feet in diameter, nearly 6 feet wider than the previous Beluga. Sheet thickness ranges from 1/10 to 1/4 inch. Each panel is reinforced with 30 stringers. Bulkheads are placed every 20 inches. Everything's riveted and bolted with titanium bolts, torqued to 90 foot-pounds. The cargo door, an engineering marvel. Stelia Rochefort, France. 33 feet long, 26 feet high. Area nearly 1,500 square feet. like a basketball court standing vertical. Weight 3.1 tons. Frame made from titanium alloy, Ti6Al4V. Titanium handles the loads. 24 latches hold the door, 12 on each side. Each latch clamps down with 3 tons of force. The door opens with 4 hydraulic cylinders, piston diameter 4.7 inches, pressure 4,000 psi. 3 minutes to open, 4 to close. Inside the door, hundreds of yards of wiring and hydraulic lines. They shipped the door from Rochefort to Toulouse on a barge, the same one that carried A380 sections. By sea to Bordeaux, by river to Langon, then 125 miles by road. The tail section, modified by Spain's Aeronova in the Basque Country. The vertical stabilizer increases by 50%, from 33 to 50 square feet. The massive bloated fuselage creates serious drag. You need stability. They add vertical end plates to the horizontal stabilizer, plus 2 ventral fins under the tail. 5 vertical surfaces total instead of 1. Everything's made from composites, carbon fiber. Layers of carbon fabric soaked in epoxy resin, laid in a mold and into the autoclave. 360 degrees Fahrenheit, 100 pounds per square inch, 8 hours. The composite fin weighs 1,300 pounds instead of 2,000 aluminum. December 2016, Toulouse. Line L34, a hangar spanning 130,000 square feet. Final assembly of the first Beluga. Lower fuselage with wings from an A330 goes on the jig. From above, a 50-ton crane lowers the expanded upper fuselage. They mate the perimeter. Hundreds of bolted connections. They drill quarter-inch holes through both sections at once, tolerance plus or minus 0.04 of an inch. Bolts get torqued with computer-controlled wrenches. The joint sealed with polysulfide compound, works from -76 to +250 Fahrenheit. They mount the nose section, tail, vertical stabilizer. 3 months of work. Meanwhile, the guts. 50 miles of wiring in bundles of 50 to 100. 2,000 feet of stainless hydraulic lines. Pressure 4,000 pounds per square inch. 12 fuel tanks. 37,000 gallons of kerosene. March 2018. Engine installation. 2 Rolls-Royce Trent 700s. Each one weighs 12.3 tons. Thrust? 320 kilonewtons, 72,000 pounds of force. Fan diameter? 9 feet. 24 composite blades with titanium leading edges. The engine mounts to the wing through a titanium pylon with 4 bolts, each 1.9 inches in diameter. Torque? 2,950 pound-feet. 37 connections to each engine. Fuel, electrical, hydraulic, pneumatic. April through June, ground testing. 200,000 checkpoint inspections. Every sensor checked, every actuator verified. Flight control checks. Elevators deflect 25 degrees up, 15 down. Ailerons, 25 up, 15 down. Laser sensors monitoring. Accuracy to within 0.5 degrees. July 19, 2018. Blagnac, Toulouse. First flight, crew of 6, 150 sensors recording 200 parameters 1,000 times per second. Takeoff thrust 96%. Turbine exit temperature 2,700 degrees. Fuel burn 12 tons per hour. 120 knots, 222 kilometers per hour. Nose wheel liftoff. 140 knots, main gear liftoff. Climb rate 1,000 feet per minute. Flight level 350, 35,000 feet. Cruise speed 0.69 Mach, 466 miles per hour. 4 hours, 20 minutes airborne. Landing nominal. Next up, flight test program. 200 flights, 700 hours. Maximum weight with ballast, 51 tons. Single engine flight. Crosswind landing at 30 knots. Minus 22 in Sweden, plus 113 in Spain. Everything works. November 13th, 2019. Type certificate. The Beluga cleared for flight. January 9th, 2020. First commercial flight. Toulouse, Bremen, Toulouse. Cargo, 2 A350 wings, each 105 feet long, 21,000 pounds. Before, 2 flights with the old Beluga. Now, 1. Loading 70 minutes. Wings roll in on a trolley along floor tracks. 24 tie-down points with straps. Flight 1 hour 40 minutes. In Bremen, they unload the wings, load A320 fuselage sections, fly to Toulouse. 3 to 4 flights a day, 6 days a week. 1,000 flights a year across 6 aircraft. Without the Beluga, Airbus wouldn't build a single plane. Wings made in Great Britain, tails in Spain, fuselages in Germany, final assembly in Toulouse and Hamburg. The Beluga, a flying assembly line. Europe's industrial artery. 1 billion euros program cost, 167 million per aircraft, 30 years of service, 60,000 flight hours. If this was interesting, hit like. Did you know about the Beluga? Write in the comments. Subscribe. Here we show you factories you never knew existed.
The fastener industry is a true empire worth over $90 billion annually. And its flagship products? Massive bolts and nuts that hold our entire industrial infrastructure together. They're not just chunks of steel with machined threads, they're the result of a complete process involving metallurgy, high-pressure forging, heat treatment, and incredibly rigorous mechanical testing. One tiny deviation in material quality, shape, or tightening force can render an entire joint unsafe. In this video, we're going inside the production line that creates giant hex bolts and nuts to show how raw steel transforms into the mechanical foundation of the modern world. The production process for heavy-duty bolts and nuts begins with one fundamental stage: cutting raw blanks. Large diameter steel bars rolled from high-strength alloy steel are fed into industrial cutting machines and divided into segments with precisely controlled length and weight. Modern cutting systems use hydraulic shears or powerful industrial saws, producing clean square cuts that don't distort the metal's internal structure. Throughout the cutting operation, coolant is sprayed directly onto the contact zone to reduce temperature, minimize friction, and wash away metal chips. This maintains cutting tool stability and ensures the blank surfaces remain clean and free from thermal damage. Typically, bolt blanks are roughly twice as long as nut blanks, because bolts require additional material to forge the load-bearing shaft and head in a single production run. During one shift, each cutting machine can process thousands of bolt and nut blanks. Each cut takes just a few seconds, yet the allowable tolerance is extremely tight, because the final shape and mechanical strength of the product depend entirely on the initial dimensions of these blanks. After the blanks are cut, the bolts and nuts move to the heating stage, but the way heat is applied to each component isn't quite the same. For nuts, the entire steel blank feeds into a continuous furnace and is uniformly heated to a temperature range of 1900 to 2100 degrees Fahrenheit. Heating the entire body allows the blank to reach a fully plastic and uniform state. So during forging, the metal can flow evenly inside the die and form a solid hexagonal body before the internal hole is drilled and threads are cut. Temperature is tightly controlled to prevent surface burning while ensuring the core remains soft enough for proper forming. Bolts, however, are heated differently. Instead of heating the entire blank, only the head portion of the steel rod passes through an induction heating system. In a matter of seconds, the front end reaches forging temperature and glows bright orange-red, while the shaft behind it stays significantly cooler. This localized heating method concentrates energy exactly where the hex head needs to form, reduces overall energy consumption, and preserves the mechanical structure of the bolt shaft, which is the primary load-bearing section of the fastener. Right after reaching forging temperature, the blanks are transferred directly into the hot forging zone for shaping. For nuts, the entire evenly heated blank is placed inside a closed forging die, where a high-powered hydraulic press forces the metal to flow according to the die's shape, forming a solid hexagonal body. Under this intense compression, the metal densifies, and its crystalline grains reorganize into a tighter structure, making the steel denser and more uniform. Between each press cycle, the forging die is sprayed with a layer of high-temperature coolant and lubricant. This helps control heat, reduce friction, and protect the die surface during continuous operation. For bolts, the forging process focuses on the head section that was induction heated. The blank is positioned so the hot end sits precisely inside the die, and the press applies force, causing the metal to flow outward, forming the hexagonal head. At the same time, the die is also sprayed with the same type of high-temperature lubricant used in nut forging. When the fluid contacts the hot die, it instantly vaporizes and creates a temporary protective film. This prevents metal adhesion and ensures the bolt head forms cleanly, with sharp, clearly defined edges. Right after forging, both the bolts and nuts are dumped straight into large steel containers for natural cooling in the open air. For big components, this cooling stage typically runs anywhere from 30 to 60 minutes, and can take even longer if the steel mass is particularly heavy. This slow cooling method prevents thermal shock, minimizes the risk of microscopic cracking, and keeps both the shape and the internal structure of the metal stable before the parts move on to the next production stages. Once fully cooled, the bolts and nuts are transferred to the surface cleaning stage. At this point, they're typically loaded in bulk into rotating drum cleaners or vibratory tumbling machines. The rotating drum moves slowly and steadily, creating mechanical friction across the entire surface of the bolts and nuts. This process sharpens the hex edges and leaves the metal surface clean, dry, and uniform. In large-scale production lines, each batch can handle anywhere from a few hundred to several thousand parts at once. Tumbling time usually ranges from a few minutes to several dozen minutes, depending on the size of the parts and the level of oxide scale stuck to their surfaces. Once the surface is cleaned, the bolts and nuts move to the identification marking stage. For nuts, markings are stamped directly onto the hexagonal body, while for bolts, markings are placed on the top face of the head. These symbols indicate the strength grade, technical standards, and manufacturer of each part. They function as an official ID card, mandatory for bolts and nuts to be approved for use in industrial structures, heavy machinery, and large-scale construction projects. Once they've achieved their final shape and received their identification markings, bolts and nuts enter one of the most critical stages of the entire process: thread machining. The threading process for bolts typically begins with a light finishing turn on the shank to achieve a precise diameter and a sufficiently smooth surface. On the lathe, the bolt is firmly clamped and rotated at a steady speed, while the cutting tool simply glides over the surface to correct dimensions before threading. After this, the workpiece is transferred to a thread rolling machine, where 2 or 3 thread rolling dies, engraved with the precise thread profile, press against the shank under high pressure. Thread rolling is a cold forming process that doesn't remove material but rather deforms the surface of the shank, creating threads through plastic flow of the metal. This produces stronger threads with improved fatigue resistance compared to threads cut by a cutting tool. For nuts, threads are created through the tapping method. First, a specialized drill bores a vertical hole through the center of the hexagonal body. Then a tap, a rotating cutting tool with external threads is inserted into the hole. As it advances, the cutting edges of the tap shave material from the hole wall, forming a precise internal thread profile. During the tapping operation, cutting fluid is continuously supplied to cool the cutting edges, lubricate contact surfaces, and flush away metal chips. Once threading is complete, both bolts and nuts move on to final quality control. First up are geometric checks: diameter, thread pitch, thread depth, concentricity, and sharpness of the thread profile. Threads must match standard thread gauges perfectly. Even the tiniest deviation means rejection. Next come mechanical tests including surface hardness, tensile strength, and torque resistance. Only after passing all these tests do bolts and nuts move to packaging. At this stage, the products are no longer semi-finished parts. They're full-fledged structural components, ready to ship to construction sites, power plants, steel bridges, or drilling rigs, where every bolt and nut will be responsible for holding together massive industrial systems. From raw steel rods through cutting blanks, heating, forging, thread cutting, inspection, and packaging, giant bolts and nuts complete a manufacturing journey that's precise down to the tiniest details. If you find this journey fascinating, hit that like button to support the video, drop a comment to share your thoughts, and subscribe to the channel to keep exploring the production lines that quietly keep our modern world running.
Every year, aircraft around the world cover more than 25 billion miles. That's roughly 26,000 trips around the Earth. And it's all thanks to the heart of aviation, the turbofan engine. Inside, there's a genuine inferno where temperatures reach over 1,100 degrees Celsius. But how can a machine made of metal survive where steel melts? How do they craft blades with micron-level precision that spin faster than a bullet? And why are some components today literally grown from powder using lasers? Stay with me till the end, and you'll discover a secret that'll forever change how you think about engineering. Turbofan engines that power the giants of the sky, Boeing and Airbus aircraft, seem like something out of science fiction. Yet they're the genuine embodiment of engineering brilliance. How do you assemble these remarkable machines from tens of thousands of parts and materials like pieces of a puzzle? Ordinary metals simply won't do for their manufacture. The engine must operate in conditions where temperatures can exceed 1,100 degrees Celsius. It's a proper inferno, and ordinary steel simply wouldn't cope. This is where titanium alloys enter the picture. Lightweight, robust, and capable of resisting melting in extreme heat. And for the hottest zones of the engine, they use nickel-based superalloys. Such extreme temperatures arise from the fuel combustion process in the combustion chamber. During engine operation, aviation fuel, typically kerosene, mixes with air and ignites, creating hot gases. These gases literally accelerate to extraordinary speeds and temperatures, over 1,100 degrees Celsius, sometimes reaching 1,500 in modern engines. This level of heat is essential to achieve maximum efficient thrust. That is, the hotter and faster the gases, the stronger the energy flow that drives the turbine and propels the aircraft. Here lies the principal challenge. The engine must not only withstand these extreme conditions, but also operate reliably. You know what's remarkable about the engine manufacturing process? Even individual components, such as turbine blades, are crafted with micron-level precision. For instance, blades are cast in a vacuum to ensure there isn't even the slightest crack inside. Some are formed to have a single crystal structure, meaning the metal has not a single seam. But that's not all. Three-dimensional printing? Yes, that's used too. For instance, for complex components that are impossible to create through traditional casting. Turbine blades are the engine's heart. They operate in the hottest zone and convert the energy from hot gases into rotational movement. First, a blade model is created from wax. Then the show begins. In a special furnace, superalloys are melted, composed of nickel, chromium, and other metals capable of withstanding temperatures above 1,100 degrees. This molten metal is poured into a ceramic mold. But the secret lies not only in the material, but also in how it's done. To ensure the blade withstands tremendous temperatures and stresses, it's often cast as a single crystal. This means the entire piece of metal has no seams or micro cracks. Why does this matter? Seams or micro cracks in such conditions are like a minefield. One error and the blade fails. Single crystals are grown through very gradual cooling. Once the metal cools, the ceramic mold is broken away and the blade undergoes thorough grinding. A special heat-resistant coating may be applied to the surface. And so, each blade is inspected individually. If there's even the slightest defect, it doesn't proceed further. Fuel injectors, combustion chamber components, or even compressor blades in aviation are manufactured using three-dimensional printing. For instance, GE Aviation prints injectors for their engines that weigh 25% less but are 5 times stronger than traditional ones. Layer by layer, from powder and light, components are created that allow aircraft to fly faster, further, and more efficiently. First, engineers create a digital three-dimensional model of the component with maximum precision. Here, every curved surface or cavity matters. Why? Because these components often operate in places where a millimeter can change everything, from engine efficiency to its reliability. Instead of the usual chunk of metal, they use ultra-fine powder here, for instance from titanium, nickel, or Inconel. It resembles sand, but with particles so minute they're barely visible to the naked eye. The powder is poured into a special reservoir, and it becomes the building material. The printer's working principle is straightforward yet brilliant. It melts the powder using a laser or electron beam. The laser heats the powder to such a temperature that it literally fuses into a uniform metallic structure. Then the next layer of powder is applied and the process repeats. This method is called selective laser sintering or melting. And here's what's splendid. Three-dimensional printing allows the creation of even the most complex geometrical forms. For instance, components with internal cooling channels that simply cannot be manufactured through casting or milling. You see, in traditional manufacturing, you often need to create a large component first, then cut away everything superfluous. The resulting component isn't quite ready yet. After printing, it undergoes heat treatment, heated and gradually cooled to relieve internal stresses in the metal. Then comes final grinding, polishing, or mechanical processing if precision needs correcting. And naturally, each component passes rigorous testing. After all, this is serious business. If a component can't bear the load, the consequences could be catastrophic. Engine assembly takes place in an enormous hangar, where every square foot is occupied by tools, engine parts, and people in overalls. Everything begins with the engine casing, resembling a gigantic metal cylinder. This is the skeleton to which all other parts will be attached. The casing is crafted from titanium or nickel alloys, as it must withstand tremendous loads. Engineers work like watchmakers. The casing is secured in an enormous machine to ensure everything is absolutely straight. Next come the compressors, several rows of blades responsible for compressing air before feeding it into the combustion chamber. Blades are installed one after another. Each is inspected manually. Following the compressors comes the turbine stern. Next, the combustion chamber is installed, the engine's genuine inferno. Here, compressed air mixes with fuel and burns. Engineers install special injectors that ensure uniform fuel delivery. And here, everything must be perfect. An incorrect injector angle, and the engine could lose efficiency or even fail. Running through the entire engine is a central shaft, a sort of backbone. At one end of the shaft, the fan is mounted in the form of an enormous wheel at the engine's front, whilst at the other end sits the turbine. To install the shaft, they employ special robots. Once the engine's internal section is assembled, external systems are added. Fuel pipes delivering combustion to the combustion chamber. The oil system, ensuring lubrication of all moving parts. And electronics, because the engine is literally packed with sensors monitoring temperature, pressure, revolutions, and much more. These elements are secured using cables, tubes, and bolts that must withstand not only vibration, but also extreme temperatures. After assembly is completed, the engine isn't dispatched to an aircraft straight away. First, it's mounted to a test stand where real flight conditions are simulated. Once the engine passes all tests, it's disassembled, the principal components are inspected once more, and then it's assembled definitively. The finished engine is packaged and transported to a Boeing or Airbus factory where it becomes part of a new aircraft. So there you have it. Component by component, engineers create the aircraft's heart, capable of carrying thousands of passengers across continents. Isn't that a modern masterpiece? Do write and let me know if you'd like to see more videos like this. Every year, the world produces over 1 billion new tires, and just as many worn-out ones end up in landfills. Just imagine, in the United States alone, over 250 million tires are recycled annually, saving the planet from mountains of rubbish. But where do these black rings go after they've served their thousands of miles? They don't simply vanish. They pass through fire, steel, and grinding machines to be born a second time. And what's most captivating, we don't even realize that every day we walk on their second life. Stay till the end, because there I'll reveal a secret that will forever change your perception of an ordinary tire. So today, we're heading to a cemetery of automobile tires. Hectares of land buried under mountains of black rubber rings. These are the silent veterans of the roads, which have rolled their thousands of miles and now lie here, seemingly useless to anyone. But this isn't the end of their story. It's merely the beginning of their remarkable reincarnation. We'll trace how these worn, dirty chunks of rubber pass through a series of brutal yet high-tech trials to be reborn as the soft, springy heart of a modern sports stadium. Americans have learned to give a second life to the overwhelming majority of tires. The recycling rate for old tires in the U.S. currently exceeds 85%. This means that over 250 million tires annually avoid landfill and are sent for rebirth. Part of them are burnt as highly efficient fuel. Part are used in civil engineering, but a significant and ever-growing quantity is transformed into rubber crumb. At this tire graveyard operates a machine resembling a steel tyrannosaurus. It's an industrial shredder. An enormous loader grabs an entire handful of old tires and tosses them into the steel jaws of this machine. Inside it, with a deafening screech, two massive shafts with thick, sharp hooks rotate. They seize the tires with relentless force and tear them to pieces with an incredible crash. Inside every tire is a steel belt, a robust framework of steel wire. During tearing, this belt is released, transforming into a glittering web of steel threads mixed with rubber chunks. This chaotic mixture of rubber and steel moves further along the conveyor. And here, an industrial, powerful, enormous magnet enters the game, rotating above the stream of shredded material. Like a fridge magnet, but 1,000,000 times stronger. It extracts all the steel threads from the rubber mass. With grinding and clanging, the steel belt sticks to the magnet and is dumped into a separate container. This steel will then be sent for remelting, whilst our purified rubber continues its journey. But it's still too large. Next stop, the granulator. During this process, another tire component is released, textile cord. These are nylon or polyester fibers that gave the tire additional strength. These light, fluffy fibers need removing. For this, rubber granules pass through a system of vibrating sieves and air separators. Powerful air streams literally blow away the light textile fluff, leaving only clean, heavy rubber granules. Now we have clean but still rather large material. To become stadium surfacing, it needs transforming into crumb. For this, granules are sent for final grinding, often in so-called cracker mills. As a result of this process, we finally obtain what everything started for, rubber crumb. This is a uniform, free-flowing mass resembling black caviar or coarse sand, where each particle size is just a few millimeters. This crumb is carefully sieved to guarantee perfect size uniformity and packed into enormous bags weighing a ton each. Its journey from dirty tire to clean, high-tech raw material is complete. And now, let's transport ourselves to where this black crumb will find its true calling, construction of a new stadium. Workers roll out huge rolls of artificial turf over a perfectly leveled gravel base. But for now, they look dreary and lifeless, pressed against the base. For them to stand up and resemble real grass, they need support. And here, a special machine enters the pitch, resembling a large fertilizer spreader. A process called infill begins. First, the machine spreads an even layer of fine, rounded quartz sand across the entire pitch. It's heavy and settles at the very base of the carpet, acting as ballast so the turf doesn't shift. And following the sand, our main hero is poured onto the pitch, black rubber crumb. The machine distributes it just as evenly across the entire surface. And here, the main transformation occurs. It's like running on 1,000,000,000 tiny trampolines. This dramatically reduces the load on athletes' joints and makes falls far safer. The final touch is combing the pitch. A special machine with an enormous brush drives across the turf, carefully mixing sand and rubber crumb and combing them deep down to the very base, forcing every blade of grass to stand perfectly upright. And now, when the work's complete, before us appears a perfectly green, springy, and safe pitch. And none of the players running on it might guess that beneath their feet lie millions of particles from old automobile tires. To create one standard pitch for American football or soccer requires on average between 20,000 and 40,000 old car tires. Just think about it. A single pitch completely devours an entire mountain of rubber waste. And how many such pitches are there in the country? Currently in the U.S., there are over 13,000 artificial turf pitches in schools, colleges, parks, and professional arenas. And now simple maths. If we take even the minimum figure of 20,000 tires per pitch, it turns out that in sports pitch surfacing across the country alone, over 260 million old tires have found their new home. Natural turf is a very finicky thing. It needs constant mowing, watering, fertilizing, and giving it rest. On average, a natural pitch can withstand no more than 20 hours of play per week. And a pitch with artificial turf? It can operate 24 hours a day, 7 days a week, in rain and heat. And now about water. One artificial turf pitch can save between 500,000 and 1 million gallons of water annually. That's the amount of water an average family uses over several years. Add to this savings on fertilizers and lawnmower work, and the benefit becomes obvious.
Ready to explode with curiosity? In this video, we're throwing open the secret doors to the world of fireworks and firecrackers you never knew existed. Stick with us and you'll see how the magic of the brightest explosions is born from simple gunpowder. Discover the wild history of their creation and learn the unusual secrets of pyrotechnic masters. How do they create explosions in every color of the rainbow from ordinary black powder? Why can a single firework contain over 1,000 pellets, each burning its own unique color? What metals create red, green, and blue fire in the sky? And most importantly, why do masters remove even their wedding rings before work? And how can one stray spark destroy an entire lab? You'll find out how many hours it takes to create one professional firework, which countries produce 90% of the world's pyrotechnics, and what one epic New Year's Eve show costs. This story will make your heart race. Watch until the end, because the most important part is coming. Stay with us until the finale and you'll learn something that will flip your perspective. Don't miss it. Firecrackers. These are the more zippy guys in the pyrotechnic family. Their thing is sound, not spectacle. Even though they're simpler in design, they create the same magic, noise, and adrenaline. Like fireworks, the foundation of firecrackers is black powder, but here everything's a bit simpler. The main goal? Hit the right balance for a powerful bang without the extra special effects. Typically, a firecracker has a powder mixture, a casing, and a fuse. We'll talk about the filling later, but for now, let's learn a bit about the casing. It's a paper or cardboard cylinder that holds everything together. The material needs to be strong enough to contain the explosion until the moment of rupture, but not so strong that it creates dangerous shrapnel. The fuse is the most crucial element. It kicks off the explosive process. This could be a thin cotton cord soaked in chemicals, or more modern ignition mechanisms. The word firecracker comes from the French pétard, meaning explosion. Firecrackers, like fireworks, have Chinese roots. How do they make firecrackers? All components for the gunpowder mixture are carefully weighed and mixed to achieve the perfect consistency. Precision is critical here. Too much potassium nitrate and the explosion becomes uncontrollable. Too little and the firecracker won't ignite. Paper or cardboard tubes are cut to the required length, then filled with the gunpowder mixture. Typically, the casings have sealed ends to create the necessary pressure for detonation. At the top of the firecracker, they create a small opening where the fuse is inserted. It's secured using glue or special putty. The bottom and top edges of the firecracker are tightly sealed, usually with glue or heat sealing. This ensures safe storage and transportation. Next, firecrackers undergo rigorous testing. Manufacturers check sound levels, ignition speed, and blast quality. Not all firecrackers are created equal. Cheap firecrackers often have uneven filling, weak sound, and a higher risk of failure. They use lower quality materials like regular paper instead of cardboard. Quality firecracker casings are made from strong yet lightweight material. The gunpowder mixture is evenly distributed for a consistent effect. Fuses have precise burn times to give users enough time to move to a safe distance. Making firecrackers is no joke. Pyrotechnic factories have strict safety rules. Workers operate in small groups, wear anti-static clothing, and handle minimal amounts of mixture at any given time to reduce the risk of accidental explosions. Why are firecrackers so loud? This question often sparks curiosity. The thing is, a firecracker explosion isn't just a chemical reaction. It's the release of massive energy in a confined space. When gunpowder burns, it releases hot gases that rapidly expand, creating a powerful shock wave. And since a firecracker's casing is tightly packed, that wave is accompanied by the signature bang. Originally, firecrackers were used to scare off evil spirits, and only later did they become a popular form of entertainment. Making fireworks also requires mixing gunpowder with other components first. If gunpowder is the engine of the firework, then the other substances are the artists. They create the explosion of color, light, and shape. To create bright sparks, we need metal powders. That's aluminum, magnesium, titanium shavings. For vivid colors, they use metal salts like strontium, barium, copper, and sodium. Potassium nitrate, perchlorates, and charcoal amp up the explosive energy. After all, they're the oxidizers in fuel. And to hold all the components together, you need binding agents. Water-soluble glues, for example. Each component is first ground down into the finest powder. Imagine gleaming metallic particles dancing in the light as the craftsman preps them for mixing. The powders are so light, it's like they could just hang in the air like magic dust. The most important part begins when the ingredients go into the mill with ceramic or wooden balls. These balls rotate smoothly, grinding the mixture to perfect uniformity. The rustling and gentle tapping create their own rhythm, a sound that reminds you an explosion of colors is being born. When it comes to mixing ingredients by hand, traditional manufacturers approach the stage with reverence. Specialists carefully and slowly mix the ingredients with wooden or copper paddles. Why so slowly? Because even one accidental spark can trigger an explosion. The mixture looks like shimmering sand, where each component has its role. To prevent accidental explosions, the mixture is often moistened. Water doesn't just make the process safer, it adds mysterious alchemy as the gunpowder and dyes form tiny granules. The slightest mistake can lead to tragedy. You know what pyrotechnics masters do before starting work? They remove all metal objects, even rings, to avoid sparks. In many labs, cell phones are strictly banned, and clothing is chosen from anti-static materials. Even the air matters. Facilities maintain controlled humidity so the mixtures don't dry out and become explosive. Before packing the mix into a shell, craftsmen test how it burns. Flame bursts from a tiny sample and everyone in the room holds their breath. Will this be the perfect shade of blue? Are the sparks bright enough? It's like a dress rehearsal before the big show. Creating shapes and colors, that's the most exciting part of production. Want a heart or a star in the sky? It all depends on how the stars are arranged, those little pellets packed with special compounds. Where do those brilliant reds, greens, and blues come from? Chemical compounds. For instance, barium creates green, strontium gives you red, and copper produces blue. Once all the components are prepped, the next crucial step is loading the shell, where the heart of the firework comes to life. This is where the explosive mix and colorants transform into a finished product, ready to paint the night sky in every color of the rainbow. The shell is the casing that holds all the fireworks components together. It's made from a special material capable of withstanding high pressure and temperature, yet light enough to soar into the sky. Cylindrical shapes are perfect for creating crisp patterns like rings, chrysanthemums, or peonies. Spherical shapes create symmetrical and three-dimensional effects, like a ball exploding with hundreds of sparks. The process of filling the shell is extremely important, because proper component placement ensures the desired effect. First, they take cylindrical or spherical blanks, usually made from cardboard, plastic, or special paper soaked in fire-resistant substances. The sphere typically consists of two hemispheres that are later joined together. It's crucial that the shell be perfectly airtight. This guarantees the burst happens at the right moment and with the right force. The gunpowder charge, as the main propellant, is positioned in the center of the shell. It's responsible for lifting the firework into the air and detonating it properly. Colorants and specialty mixtures are placed around the charge. Each star element is laid by hand or with specialized machines. Star elements are the pellets that burn in the sky. For spherical shells, these stars are arranged evenly to form a perfect sphere when detonated. In cylindrical shells, charges are often layered or shaped into specific patterns, depending on the intended effect. One standard spherical firework contains an average of 200 to 300 pellets. In large multi-layered shells, there can be over 1,000. To ensure the firework detonates at the right moment, a delay fuse is added to the shell, a small tube filled with a special compound that burns slower. The timer connects to the main charge, providing a delay between the rocket's launch and the explosion in the sky. After all elements are positioned, they're secured with a bonding compound or paper dividers. This is crucial so none of the components shift during launch. The casing is additionally wrapped with strong thread or glue to give it rigidity. Producing a single large professional firework can take up to 4 hours considering the manual assembly and inspection. For a large-scale show with several thousand shells, pyrotechnicians work for several months. The spherical shape is a classic in pyrotechnics. It ensures even distribution of stars during the burst, creating the effect of a perfect circle. Filling such a shell requires even greater skill. Each star is manually positioned around the central charge, and here everything depends on the master. How the components are arranged is how the burst will look. For example, to create a smiley face in the sky, the pellets are laid out in the shape of a face. When the gunpowder explodes, the pellets scatter precisely in the shape of the intended pattern. Every year, the world produces over 200,000 tons of fireworks. The production leader is China. It accounts for roughly 90% of global output. For major holidays such as US Independence Day or New Year's in Sydney, up to 10,000 individual fireworks are launched in a single night. This can last over 20 minutes, and the cost of a single show sometimes reaches $5 million. What if I told you there's a metal that can't be destroyed by fire, pressure, or time? A material without which aviation would grind to a halt, lights would go dark, and rocket engines would fall silent. And here's the thing, it's so rare that the entire world is competing for every single gram. Tungsten has the highest melting point of any metal on Earth, a staggering 6,192 degrees Fahrenheit. That's a temperature at which most other metals would have long since turned to vapor. Annual global tungsten production ranges from 85 to 100,000 tons per year. But here's what's striking. Up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number, showing just how valuable it is. Total global tungsten reserves are estimated at roughly 3 to 3.5 million tons, nowhere near the reserves of iron or aluminum. But here's what really matters. By the end of this video, you'll learn a secret about tungsten that the industry hides and almost nobody talks about. Something that will flip your understanding of the metal holding civilization together. Picture a massive underground mine somewhere in Vietnam, China, Russia, or Canada. The world's biggest tungsten producers. Deep in the Earth's belly, hundreds of feet down, lie ores containing tungsten. Not pure metal, but complex minerals, wolframite and scheelite. Wolframite is a compound of iron, manganese, and tungsten. Scheelite is calcium tungstate. Geologists use various methods to identify and assess tungsten ore deposits. Then, using powerful drilling rigs and explosives, the ore is extracted from deep underground. It's tough, dangerous work, requiring high-tech equipment and strict safety standards. Thousands of tons of ore get hauled to the surface daily by massive underground trucks. Powerful blasts shatter the rock, exposing the valuable ore. It's like a controlled earthquake in miniature. After the blast, the ore gets loaded into haul trucks with capacities up to 300 tons and transported to the processing plant. After extraction, the ore goes to a processing plant. Here it undergoes several stages to separate valuable wolframite or scheelite from other rocks. First, the ore is crushed in crushers and mills into a fine powder. Massive jaw crushers with deafening roars break down car-sized chunks into fist-sized pieces. Then the crushed ore enters ball mills, giant rotating drums filled with steel balls. In these mills, the ore is ground into an extremely fine powder, almost like flour. Next, various enrichment methods are applied, such as gravity separation, magnetic separation, and flotation. Gravity separation uses the difference in density. Tungsten minerals are heavier than waste rock. Magnetic separation separates weakly magnetic wolframite particles from non-magnetic impurities. Flotation is a process where the ground or powder is mixed with water and special chemical reagents in large tanks. These reagents selectively attach to tungsten mineral particles, making them water repellent. Air is then pumped through the mixture, creating millions of tiny bubbles. The tungsten mineral particles latch onto these bubbles and rise to the surface, forming a foam. Other unwanted minerals stay at the bottom. This enriched foam is collected. These processes yield a concentrate containing 60 to 70% tungsten trioxide, which is an intermediate form. The resulting concentrate is then processed at metallurgical plants to obtain pure tungsten. This is a complex chemical process that can involve alkaline leaching, precipitation of ammonium paratungstate, and its subsequent calcination to produce tungsten oxide. The concentrate is dissolved in alkaline solutions at high temperatures. Ammonium paratungstate, an intermediate compound, is then precipitated from the solution. This compound is calcined at temperatures around 1100 to 1500 degrees Fahrenheit, producing tungsten oxide, a yellow powder. Tungsten oxide is then reduced to metallic tungsten by heating it in a hydrogen atmosphere at temperatures ranging from 2000 to 3300 degrees Fahrenheit. Inside specialized furnaces, tungsten oxide is heated in a stream of hydrogen. The hydrogen strips away oxygen from the tungsten oxide, releasing pure metallic tungsten. The result is a fine gray tungsten powder, the foundation for every product that follows. It's from this powder that tungsten rods, bars, and other blanks are formed through sintering. The tungsten powder is pressed under high pressure into the desired shape, then sintered at extremely high temperatures in a hydrogen atmosphere. This allows the powder particles to bond together, forming a dense, durable material. Sintering temperatures can reach 5400 degrees Fahrenheit. At that temperature, the powder particles begin to fuse, creating a monolithic structure. The process takes place in furnaces with controlled atmospheres to prevent oxidation. One of the most critical applications is the production of hard alloys known as tungsten carbides. These alloys, combining tungsten with carbon, plus cobalt or nickel as a binding agent, rank among the hardest man-made materials. Tungsten carbide is created by heating tungsten powder with carbon at temperatures around 2500 to 2900 degrees Fahrenheit. Tungsten carbide crystals form, which are then ground into powder. This powder is mixed with cobalt or nickel, serving as a binder, pressed into molds, and sintered. Tungsten carbides are used to manufacture cutting tools, drill bits, milling cutters, lathe tools that can machine the hardest metals and alloys. Without tungsten carbides, modern mechanical engineering, metalworking, and oil and gas extraction would be impossible. 2 pounds of tungsten can become a drill bit capable of boring thousands of feet through rock, demonstrating its incredible efficiency. Tungsten is also widely used in the military industry for manufacturing armor-piercing shells and bullet cores. Thanks to its high density and hardness, tungsten alloys have excellent penetration characteristics, providing high effectiveness against armor. It's also used in heavy armor plating and counterweights. In electronics and electrical engineering, Tungsten is irreplaceable. It's used to produce filaments in incandescent bulbs, welding electrodes, electrical contacts, and other components requiring high heat resistance and electrical conductivity. Because of its high melting point, it's used in the space industry for components subjected to extreme temperatures. High-temperature alloys containing tungsten are used in aircraft engines, turbines, and other devices operating under conditions of extreme heat. Alloying with tungsten increases the heat resistance of other metals. In medicine, tungsten is used in manufacturing X-ray tubes thanks to its high atomic number, which effectively blocks X-rays. It's also used in radiation shielding, similar to lead, but with lower toxicity. Plus, tungsten is used to create ballasts and counterweights in race cars, aircraft, and yachts thanks to its high density. It's also a component in certain jewelry pieces because of its hardness and scratch resistance. Tungsten is one of the least abundant elements in Earth's crust, which makes its mining and production especially valuable. Global tungsten reserves that are economically viable to mine are estimated at roughly 3 to 3.5 million tons. However, when you factor in potential but not yet explored resources, the total volume could be significantly higher. This is, of course, incomparably less than reserves of metals like iron or aluminum, which underscores its strategic value. Annual global tungsten production, measured in tons of pure metal or tungsten oxide equivalent, fluctuates, but in recent years it's been approximately 85 to 100,000 metric tons per year. This figure includes both primary extraction from ores and recycling, which is becoming increasingly important. Imagine being able to take a worn-out tool that's already served its purpose and turn it back into something new, without spending energy and resources mining ore from scratch. That's exactly what happens with tungsten. Tungsten recycling is among the most advanced and efficient of all metals. By various estimates, up to 40% of all tungsten consumed worldwide comes from recycled material. That's a massive number, demonstrating its value and economic viability. Where does used tungsten come from? The main source of secondary tungsten material is, of course, spent cemented carbides. Those cutting tools, drill bits, and milling cutters made from tungsten carbide. After intensive use, they wear down, lose their edge, or break. Instead of tossing them in a landfill, they're collected and sent to recycling plants. Other sources include tungsten-containing scrap metal, leftovers from tungsten product manufacturing, plus certain electrical contacts and wires. Recycled tungsten is significantly cheaper to produce than primary metal because it eliminates the expensive and energy-intensive stages of ore mining and initial processing. Recycling dramatically reduces tungsten production's environmental footprint. It minimizes the need for mining operations, cuts energy consumption, reduces industrial waste, and lowers greenhouse gas emissions. This makes production greener and more responsible. And so, after a journey from underground blast through grinding into powder, and through flotation with millions of bubbles, through chemical dissolution and reduction in a hydrogen atmosphere at 1800 degrees, through sintering at 3000 degrees, a metal is born with the highest melting point on Earth, capable of withstanding 6192 degrees Fahrenheit, a metal without which modern industry, aviation, aerospace, and medicine would be impossible. And the most remarkable part, nearly half of this metal is born anew from old tools, making tungsten one of the most environmentally friendly strategic materials of our civilization. Every second, the world produces 28 million tons of stainless steel. And behind the shine of every spoon, every faucet, every surgical instrument stands one metal: chromium. But here's what's mind-blowing. Chromium melts at 3,375 degrees Fahrenheit, and in the electric arc furnaces that produce it, temperatures hit 5,000 degrees, hotter than the surface of the sun. A single furnace consumes 4,000 kilowatt hours of electricity per ton of alloy. That's as much as the average apartment uses in 4 months. 80% of all chromium in the world goes into making stainless steel. But where does this metal come from? Why are 99% of the world's chromite reserves concentrated in just a handful of countries? And what happens in that hellish zone beneath the electrodes where ore transforms into molten ferrochrome? Stick around. You'll discover how black rock gives birth to the metal that makes steel immortal. Picture a massive electric arc furnace as tall as a 3-story building. 3 carbon electrodes up to 6 feet across plunge into a churning mass of glowing ore, coke, and fluxes. Between the electrode tips and the furnace floor, electric arcs crack and snap. Temperatures in this zone hit 5,000 degrees Fahrenheit. That's hotter than the surface of the sun. The air above the furnace shimmers with heat. Clouds of smoke and gas blast out from beneath the half-closed roof. Inside, real alchemy unfolds. Chromium ore mixed with coke melts down, oxygen escapes as carbon monoxide, and molten ferrochrome, an alloy of chromium and iron, flows to the bottom. This is a submerged arc furnace, and this is where most of the world's ferrochrome is born. The process runs non-stop. Fresh batches of ore and coke pour in from the top, molten metal and slag tap out from the bottom. A single furnace like this can pack 25 to 45 megavolt amperes of power. This is a monstrous amount of energy. An entire power plant runs just to melt the ore. When enough molten ferrochrome accumulates in the furnace, workers punch open the tap hole, a special opening in the furnace's side. And then the mesmerizing spectacle begins. A stream of white-hot metal and slag bursts out, flowing down a channel into an enormous ladle. The stream's temperature around 3,000 degrees Fahrenheit. The metal glows bright orange, almost white. The heat radiating from it is so intense that workers stand dozens of yards away, protected by special screens and fireproof clothing. Slag floats to the top and is drained off separately. The ferrochrome cools in massive molds, transforming into solid ingots weighing hundreds of pounds. These ingots are later crushed into pieces of the right size for sale to steel mills. But the process of obtaining ferrochrome, that's only the middle of the journey. It all begins with ore, mined deep in the earth. Chromite, the only industrial ore of chromium. It's a dark brown, almost black mineral with a metallic luster. The chemical formula? Iron and chromium oxide. Pure chromite contains 68% chromium oxide and 32% iron oxide. But in nature, perfect ores like that barely exist. Real deposits contain anywhere from 40 to 50% chromium oxide. Chromite forms in igneous rocks, in massive molten masses rising up from the Earth's mantle. The largest deposits are found in South Africa, Kazakhstan, India, and Turkey. These 4 countries account for roughly 80% of global production. South Africa is the absolute leader. Its deposits in the Bushveld complex contain 200 million tons of chromite. We're talking ore seams stretching for hundreds of miles and plunging thousands of feet deep. Kazakhstan holds reserves of 230 million tons. India? 54 million tons. Now, the story. French chemist Louis-Nicolas Vauquelin discovered chromium in 1797. He isolated it from croquat, a bright red lead chromate mineral. The mineral's vivid color inspired Vauquelin to name the metal after the Greek word chromos, color. Because chromium compounds produce stunning colors, greens, yellows, oranges, reds. A year later, in 1798, Vauquelin isolated pure chromium by reducing the oxide with carbon. Iron with added chromium was first produced in the mid-1800s, and the first use of chromium as an alloying element in steel production happened in France in the 1860s. The revolution came in 1893 when Henri Moisson smelted chromium ore with carbon in an electric furnace and produced ferrochrome. This became the foundation of the modern industrial method, which has evolved but at its core remained the same. Chromite gets mined both through open-pit operations and underground mines. Open-pit mining gets used when the ore sits close to the surface. Giant excavators strip away the soil and overburden, exposing the chromite layers. Then they blast the ore, load it into haul trucks with capacities up to 300 tons, and transport it to the processing plant. Underground mining gets deployed for deep deposits. Tunnels get driven hundreds of feet down, sometimes miles. They blast the ore, load it into mine cars, and haul it to the surface. The extracted ore? It's not pure chromite yet. It comes mixed with waste rock and other minerals. That's why the ore needs processing. First, they crush it in massive jaw crushers. Chunks the size of a car get reduced to fist-sized pieces. Then they grind it in ball mills down to the size of sand or even dust. After that comes separation, isolating the chromite from the waste rock. The main method for enriching chromite is gravity separation. Chromite is heavier than waste rock. Its density is 4.5 to 4.8 grams per cubic centimeter, while the rock is 2 to 3 grams. The crushed ore is mixed with water, creating a slurry. The slurry passes through jig machines, concentrating tables, spiral classifiers, centrifugal separators. Under the force of gravity, the heavier chromite grains settle faster, while the lighter waste rock is carried away by the water flow. Magnetic separation is also used. Chromite is weakly magnetic, but modern high-intensity magnetic separators can attract it and separate it from non-magnetic impurities. After enrichment, they obtain chromite concentrate containing 46% or more chromium oxide. This is ready-made raw material for metallurgy. The concentrate is dewatered, dried, and sent to ferroalloy plants. Lump ore is needed for ferrochrome production. Fine powder doesn't melt well in the furnace. So the fine particles get agglomerated, sintered into large chunks. They mix the concentrate with fluxes and coke breeze, moisten it, and form pellets. Then they heat it to about 2,200 degrees Fahrenheit. The pellets sinter into solid lumps a couple inches across. Now the ore is ready for smelting. At the ferroalloy plant, chromite concentrate gets mixed with coke and fluxes in specific proportions. Coke is the carbon source that'll reduce the oxides down to metal. Fluxes, quartzite, dolomite, limestone, are needed to form slag with the right composition and melting point. The charge, the mix of ore, coke, and fluxes, gets loaded into the electric arc furnace from the top through special hoppers. Loading happens continuously or in batches depending on the furnace type. The electrodes, massive carbon cylinders, are submerged in the charge layer. When they switch on the current, an electric arc forms between the electrodes and the material beneath them. Temperature in the arc zone? 5,000 degrees Fahrenheit and higher. That's enough to melt any ore. Inside the furnace, complex chemical reactions take place. Carbon from the coke combines with oxygen from chromium and iron oxides, forming carbon monoxide that rises upward. Chromium and iron are reduced to their metallic state and fuse together, forming ferrochrome. Some of the carbon dissolves into the metal, producing high carbon ferrochrome with a carbon content of 4 to 8%. Typical South African ferrochrome contains 52 to 54% chromium, 6 to 7% carbon, and 2 to 4% silicon. Ores from Zimbabwe with a higher chromium to iron ratio yield a product with 63 to 67% chromium. The molten ferrochrome and slag accumulate in the lower part of the furnace, the hearth. When enough metal has built up, they open the tap hole. Metal and slag flow into a ladle. The slag floats to the top and is poured off or skimmed away. The metal is poured into molds or cooled in special forms. Once solidified, the massive ingots are broken down by hydraulic presses or hammers into pieces of the required size. Ferrochrome production is incredibly energy intensive. A single ton of high-carbon ferrochrome burns through 2,000 to 4,000 kilowatt-hours of electricity. That's why ferrochrome plants get built in countries with cheap power, often right next to hydroelectric dams. Chromium recovery from ore hits about 90% under good conditions. The remaining 10%, it goes into slag. Slag isn't just waste. Metal particles get extracted from it using mineral processing methods, and what's left goes into construction. Ferrochrome isn't the end product. It gets shipped to steel mills where it's added to molten steel for alloying. Chromium gives steel corrosion resistance, hardness, heat resistance. Stainless steel contains 10 to 20% chromium. Average, 18%. It's chromium that forms a thin, invisible oxide film on the steel's surface, protecting the metal from rust. And so, having traveled from black rock in the Earth's depths, through quarry explosions, crushing and processing, through the inferno of an electric arc furnace at 5,000 degrees Fahrenheit, ferrochrome is born. An alloy that gives steel eternal life and shine, resistant to time and corrosion.
Every year, the world produces over 500 million tons of glass. Without it, there'd be no windows, smartphones, cars, or skyscrapers. But few people know that the journey to this perfect transparency doesn't start with glass at all. It starts with hot sand, heated in furnaces to temperatures exceeding 1,600 degrees Celsius. This isn't just manufacturing, it's modern-day alchemy. Millions of tons of sand transformed into an ocean of molten glass, floating on liquid tin to create a perfectly smooth surface. You're about to discover the secrets of this process right here. Before hot sand becomes a transparent window, it all begins in a quarry. The primary raw material for float glass is high-quality silica sand. It must be almost perfectly pure, with a silicon dioxide content exceeding 99.5%. This sand is extracted from special deposits, typically deep underground. One of the most prized is Ottawa sand from Illinois. Pale white, fine as flour, and exceptionally pure. Quarries operate like giant anthills. Excavators tear through layers of earth, whilst lorries, 40-tonners, haul the sand to crushing plants. Then comes dry screening. The sand is cleaned of stones and the slightest impurities. Besides sand, glass contains several other components. Soda ash lowers the melting temperature. It's transported from salt deposits, particularly from Wyoming, in 23-kilogram bags or in bulk. Limestone stabilizes the structure. It's supplied from quarries and ground to a dust with particles under 1 millimeter in diameter. The mix also includes dolomite, aluminum oxide, saltpeter, and glass waste, what's called cullet. Cullet reduces the energy consumption for melting by up to 25%. After initial cleaning, all components are mixed in precise proportions, which are kept as trade secrets. A giant mixer the size of a 2-story house prepares the glass flour mixture. The finished mixture is transported to production by lorry and sometimes by rail or even on barges. Storage temperature must be controlled, no moisture whatsoever. The warehouse resembles a sterile grain elevator with silos, each with a capacity of roughly 560 cubic meters. The mixture is then automatically fed into the glass furnace, where within just minutes, everything that was sand and dust yesterday transforms into a boiling ocean of glass. The mixture enters the heart of production, the glass furnace. It's a genuine industrial volcano, over 60 meters long, with temperatures reaching 1600 degrees Celsius at the melting core.
Raw materials are fed in automatically, several tons per hour. In the first 9 to 12 meters of the furnace, melting occurs. Components melt and merge into a glowing, viscous mass. Next comes the homogenization zone. The mass is stirred and matures until all bubbles and lumps disappear. And only then does it gently flow onto metal. This is where the magic begins. In the second stage, the mass enters a bath of molten tin heated to 1100 degrees. The glass literally floats on the metal, spreading into an even ribbon. Thanks to surface tension and the perfect flatness of the tin, a mirror-smooth surface forms on both sides, without polishing, without presses.
Thickness is controlled by stretching, special rollers, or electromagnetic fields either stretch or compress the glass ribbon. This way, the output can be glass ranging from 1.5 to 19 millimeters thick. The tin bath spans over 45 meters, and the glass slowly floats along it at speeds up to 7.5 meters per minute, cooling en route to 540 degrees Celsius. This is an absolutely critical moment, but even at this stage, it's not ready yet. Next comes the annealing zone. The glass ribbon passes through a long tunnel where it cools by several degrees per minute to relieve all internal stresses. Without this, the glass could later crack on its own. Its surface is like ice, smooth without a single scratch. The sheet size is impressive, up to 3 meters wide and over 9 meters long. In this state, the glass enters the cutting zone. Before it's cut, a computer scanning system analyzes the entire surface, searching for micro cracks, inclusions, stress points. Any find means that sheet's rejected. Cutting isn't mechanical anymore. Now it's laser or roller scoring. A microblade, similar to diamond, scores a line, and then gentle pressure snaps the glass precisely along that path. Sometimes sheets are cut straight to order, say 60 by 90 centimeters for construction glass or screen size for Tesla. Others go in standard formats to warehouses, where they're stored vertically on racks with rubber spacers. After cutting comes the calibration stage. Sheets are checked for thickness, geometry, straight edges. High-definition cameras scan every centimeter. Lasers analyze the corners. There are almost no human hands here, only at the final stage when workers in gloves mark the perfect sheets. In a world where glass has perfect transparency, marking is its name, passport, and craftsman's signature all in one. It's in the marking zone that each piece of glass is given its identity, where, when, by whom, and for what purpose it was created. The most common method is laser engraving. A special laser burns microscopic dots onto the surface, creating an indelible frosted inscription. Font thickness is less than 2.5 millimeters. This inscription can't be removed without damaging the glass, which is precisely why it's often used as an anti-tamper code. Sandblasting is used for decorative or premium glass. Through a stencil, abrasive is applied to the glass under pressure, forming a raised frosted mark. Then there's marking with ceramic inks. This method is used at the stage before tempering. Special paint is applied by printing, then baked at temperatures exceeding 1100 degrees. This marking is colored, noticeable, and extremely durable. It won't wash off, won't wear away, and won't fade. Marking can be either technical or branded. For instance, windows in luxury homes often proudly display the manufacturer's logo. In some projects, marking is even used for authenticity verification. For example, glass for armored vehicles or government buildings receives a serial number and QR code. The final stage is documentation. Every sheet gets a record in the system, like in a hospital. What sort of patient it is, when it was born, what properties it has, and where it's heading. This matters because glass isn't always dispatched immediately. Some batches are stored for months until their time comes.
Imagine a part so perfect it can spin for 30 years without stopping. From tiny balls just 1/8 of an inch across to giants 30 feet tall holding up wind turbines, bearings are a $120 billion a year industry. But their life begins in absolute chaos. Massive explosions, hellish fire, pressure that could crush a tank. How does raw metal become the heart of perfection? Today you'll follow the complete journey, from a quarry blast to the perfect ball spinning at 10,000 revolutions per minute. If you want to see how chaos turns into precision, subscribe to the channel. Here we show the manufacturing that builds our world. It all starts with a roar that shakes the ground for miles around. In the giant quarries of Australia and Brazil, iron ore hides in layers of rock hundreds of feet thick. Geologists turn the quarry into a chessboard. They drill boreholes 60 to 100 feet deep. Borehole diameter, 10 inches. Distance between boreholes, 16 feet. 1 square mile, 1,000 boreholes. Into each they pour explosives, a mix of ammonium nitrate and diesel fuel. Ratio 94 to 6%. Charge weight per borehole, 650 pounds. Detonation happens with millisecond delays. First borehole explodes. 20 milliseconds later, the second. 40 milliseconds, the third. The wave rolls across the entire field. In 10 seconds, they detonate 200 boreholes. They blast 3.5 million cubic feet of rock, energy equivalent to 110,000 pounds of TNT. But this isn't random chaos. This is planned destruction. Chunks of rock shoot 150 feet into the air. They fall. Dust rises over half a mile into the sky. When it settles, instead of a mountain, there lies 2 million tons of crushed ore. Giant excavators roll onto the site. The excavator bucket? 1,400 cubic feet. That's the volume of a small apartment. The bucket weighs 28 tons. One scoop? 100 tons of rock. They load it into dump trucks. Hauling capacity of each truck, 360 tons. Wheel height, 13 feet. Diameter, 11.5 feet. Weight of one wheel, 5 tons. Engine, 3,500 horsepower. Fuel consumption, 35 gallons per mile. The dump truck hauls ore to the crusher. Distance, 9 miles. Speed, 25 miles per hour. Travel time, 20 minutes. In one day, a single truck makes 30 trips, hauls 10,000 tons. 20 excavators and 60 dump trucks work the quarry. They move 300,000 tons of ore per day. That's 100 million tons a year. Crushing. Ore enters the jaw crusher. The crusher's mouth, 13 feet wide. The jaw weighs 120 tons. Jaw stroke, 12 inches. Oscillation frequency, 200 strikes per minute. Drive power, 1.5 megawatts. The crusher pulverizes yard-wide rocks into 8-inch chunks. Throughput, 2,000 tons per hour. From the jaw crusher, ore moves to the cone crusher. The cone spins inside the bowl at 150 revolutions per minute. Gap between cone and bowl, 1 inch. 8-inch pieces become 1-inch pieces. Then the ball mill. Cylinder 20 feet in diameter. Length 26 feet. Inside steel balls. Ball diameter 4 inches. Weight per ball 9 pounds. Total balls, 50,000. Combined weight, 200 tons. The mill rotates at 18 revolutions per minute. Balls drop from 6.5 feet. Impact grinds ore to powder. Particle size after milling, 0.04 inches. The thickness of a human hair. Thickness. Flotation enrichment. Ore powder gets mixed with water, creates a slurry. Solid concentration, 30%. Add reagents. Potassium xanthate, 7 ounces per ton of ore. Pine oil, 1.8 ounces per ton. Xanthate makes iron particles hydrophobic. They repel water. Pour the slurry into the flotation machine. Tank volume, 13,000 gallons. Air pumps in from below. Pressure, 30 pounds per square inch. Flow rate, 10,000 cubic feet per hour. Air forms billions of bubbles 0.2 inches across. Bubbles stick to iron particles. Lift them up. Foam forms on the surface. Reddish gray. Dense. Iron content in the foam, 67%. Waste rock sinks to the bottom. Gets pumped out and dumped in tailings. Foam scraped off with blades, sent to filtration. Vacuum filter sucks out the water. Leaves a damp mass. Moisture content, 9%. That's concentrate. Gets turned into pellets. Pelletizing. The concentrate goes to a disc pelletizer. The disc is 15 feet across, tilted at 45 degrees, spins at 15 revolutions per minute. Powder feeds onto the disc. Water's added, 3% by weight. Centrifugal force rolls the powder into balls. Pellets come out 1/2 inch in diameter, give or take 1/16 of an inch. The pellets roll off the edge onto a conveyor. Output? 300 tons an hour. 1,000,000 pellets every hour. The pellets head to the kiln. Firing temperature, 2,450 degrees Fahrenheit. 20 minutes in the heat. The pellets turn rock hard. Crushing strength, 3,500 psi. Now they're ready for the blast furnace. Blast furnace smelting. Pellets are loaded into the blast furnace. The furnace stands 105 feet tall. The throat diameter, 40 feet. The hearth diameter, 26 feet. Furnace volume, 42,000 cubic feet. Loaded in layers. Pellet layer, 3 feet. Coke layer, 20 inches. Limestone layer, 8 inches. Hot air blasts in from below. Temperature, 2,200 degrees. Pressure, 60 pounds per square inch. Flow rate, 100,000 cubic feet per minute. The coke burns, carbon monoxide releases. It strips the iron from the pellets. Temperature in the hearth, 3,600 degrees. The iron melts, flows downward, pools in the hearth. Every 4 hours they tap the pig iron. They open the tap hole. Pig iron pours out like a river of fire. Temperature at 2,700 degrees. Color, bright orange. One tap, 300 tons. In 24 hours, the furnace produces 2,000 tons of pig iron. The pig iron contains 4% carbon. That's way too much. Pig iron's brittle. Needs converter smelting. Steel production. They pour pig iron into an oxygen converter. The converter holds 350 tons. A lance descends from above. The lance is 20 inches across. Pure oxygen blasts through the lance. Pressure hits 175 pounds per square inch. Flow rate, 18,000 cubic feet per minute. Jet velocity, 1,300 miles per hour. That's twice the speed of sound. Oxygen oxidizes the carbon burns. Turns into carbon dioxide. Flame shoots out the converter's mouth. Flame reaches 30 feet high. Temperature hits 3,600 degrees. The process takes 20 minutes. Carbon content drops from 4% down to 0.7%. This is bearing steel. Grade designation SAE 52100. Chromium content 1.5%. Chromium provides hardness and wear resistance. They pour the steel into a ladle, from the ladle into molds. Out come ingots, blanks weighing 5 tons each. Ingot dimensions, 3 feet by 3 feet by 6 feet. Rolling and machining. Ingots are heated in a furnace to 2200 degrees Fahrenheit. Rolled on a mill. Rollers 40 inches in diameter. Rolling force 2,000 tons. The ingot becomes rods 4 inches across. Rod length 20 feet. Rods are cut into blanks 8 inches long. Blanks are heated to 1560 degrees. Stamped into rings on a press generating 1,200 tons of force. You get a ring with an outer diameter of 4 inches. Inner diameter, 3.1 inches. Height, 0.8 inches. Rings undergo heat treatment, heated to 1540 degrees. Held 30 minutes. Quenched in oil at 140 degrees. Cooling rate, 540 degrees per second. Tempered at 360 degrees for 2 hours. Hardness after heat treatment, 62 Rockwell. Then, grinding. The ring is clamped in a lathe chuck. The abrasive wheel spins at 100 feet per second. Removes a metal layer 0.004 inches thick per pass. Surface roughness, 0.08 millionths of an inch. That's 10 times smoother than glass. Deviation from roundness, no more than 0.08 thousandths of an inch. Balls are made by cold heading. Wire 1/2 inch in diameter is cut into 1/2 inch segments. Each segment is clamped between 2 dies. Pressure, 2 tons. The segment deforms into a sphere. You get a rough ball? It's ground between 2 cast iron discs. The discs rotate toward each other. Speed, 200 revolutions per minute. Between the discs, abrasive paste. Grit size, 40 micrometers. Grinding takes an hour. The ball shrinks by 0.012 inches. Final diameter, 0.46 inches. Deviation, plus or minus 0.004 hundredths of an inch. Sphericity, 0.08 thousandths. Roughness, 0.02 millionths of an inch. Bearing assembly. Inner ring, outer ring, 17 balls. Brass separator, lithium grease. Bearings done. It'll spin for 30 years, 1 billion revolutions. What you're witnessing here is something that would have made our grandfathers stop dead in their tracks and stare in absolute wonder. This is the forging of a massive rolling mill shaft for a steel plant weighing 5,700 pounds. That's almost 3 tons of solid steel being shaped by pure force and principles that are centuries old. The process starts with a massive steel ingot that's been heated in a gas furnace to around 2,200 degrees Fahrenheit, hot enough to glow like a miniature sun. Back in the days when American steel mills dotted the landscape from Pittsburgh to Gary, Indiana, this kind of work was the backbone of our industrial might. The forging press you're seeing here is a modern hydraulic giant capable of exerting thousands of tons of pressure. But the fundamental process hasn't changed since blacksmiths were shoeing horses on Main Street. Watch closely as the glowing workpiece gets positioned under the press. The operators, and these folks are true craftsmen, use overhead cranes and manipulators to rotate and position the workpiece with incredible precision. Every press strike, every controlled squeeze is carefully calculated. They're not just hammering hot metal, they're restructuring the grain structure of the steel, eliminating internal voids and creating a component that'll eventually face enormous forces in the rolling mill. The shaft gets worked from multiple angles, gradually taking shape. Between each pressing operation, the team repositions the workpiece, sometimes returning it to the furnace to maintain that critical working temperature. This dance between heat and pressure goes on for hours. The hydraulic press moves with deliberate force, almost gently despite its massive power. Around 5,000 to 10,000 tons of pressure compacts the steel's crystalline structure into something far stronger than the original ingot could ever be. What's fascinating is how this forged shaft will serve in a steel mill, helping shape other steel products. It's a beautiful cycle. Metal processing metal, and these shafts can last for years under extreme conditions. Today's technology, precise temperature control, computer-controlled press cycles, metallurgical analysis, ensures consistency our ancestors could only dream of. But the soul of the process remains unchanged. Heat, pressure, and the skilled hands of craftsmen who understand steel like old friends. Now here's something that combines brute force with surprising delicacy. The process of coiling a 2-inch spring bar. If you've ever wondered how these massive industrial springs are made, the ones that control freight train suspension or support heavy machinery, you're about to get a lesson. The process starts with raw stock, in this case a solid 2-inch diameter rod of heat-treated spring steel. This isn't ordinary metal. It's been precisely engineered to have the exact balance of hardness and flexibility. Too hard, and it'll snap like a pretzel. Too soft, and it won't spring back properly. Watch as the rod feeds into the coiling machine. The machine grabs one end, while a massive rotating mandrel, essentially a former, begins bending the rod around its circumference. The force required here is substantial. We're talking about permanently deforming 2-inch steel, which demands hydraulic power in the range of several hundred tons. The mandrel size determines the spring's inner diameter, and precision here is critical. As the coiling progresses, you'll notice how smoothly the rod bends despite its thickness. This is achieved through controlled feed rates and constant pressure. The machine maintains tension while rotating, creating consistent spacing between coils. Back in the 30s and 40s, this kind of work was done by hand with tremendous effort, using heat and mechanical advantage. Modern CNC systems can produce springs with tolerances measured in thousandths of an inch. What you're seeing here is one of the most reliable welding processes ever developed: submerged arc welding. This technique has been joining heavy steel since the 1930s. Here's what makes this process so special. Unlike stick welding, which your grandfather might have done in his garage, or even modern semi-automatic welding, submerged arc welding happens beneath a blanket of granulated flux. This flux, which looks almost like coarse sand, performs several critical functions. It shields the molten weld pool from atmospheric contamination, prevents oxidation, and actually contributes to the chemistry of the weld itself. The setup is mesmerizing. A continuously fed wire electrode runs through the welding head, and when it strikes an arc to the base metal, it melts both the electrode wire and the parent material, creating a deeply penetrating weld. But you can't see any of this happening, because it's all taking place under that protective layer of flux. The flux melts on top, forming a protective slag that operators chip off later. Watch the welding head move along the joint. It's typically automated for consistency. The process can deposit weld metal at rates that would make a stick welder cry with envy, 10 to 50 pounds per hour depending on the setup. That's why submerged arc welding is the #1 choice for welding thick sections in shipbuilding, pressure vessel fabrication, and structural steelwork. The beauty of this process lies in its depth of penetration. Submerged arc welding can achieve full penetration welds on steel up to 3/4 of an inch thick in a single pass. Now, let's look at modern hot forging, a process that's adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small-batch artisanal blacksmithing. The process begins with steel blanks, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion. But within seconds, a steel blank placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself. And these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2000 and 2300 degrees Fahrenheit. Depending on the steel grade, the blank is transferred to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. Excess material, called flash, gets squeezed out around the edges and is later trimmed off. What's remarkable is the speed and precision of modern forging presses, machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. Sometimes you need to bend metal that's so big it seems almost impossible, and that's exactly what a horizontal bending press specializes in, forming massive pipes that can be several feet in diameter. The problem with bending large pipes is avoiding what we call wrinkling on the inside radius and tearing on the outside radius. The system solves this through controlled hydraulic pressure applied by a precisely formed die that supports the pipe during the bending process. Watch as the massive pipe gets positioned in the machine. That positioning alone requires overhead cranes and careful alignment. The bending die, often weighing several tons itself, presses against the pipe while it's supported at both ends. The hydraulic system applies hundreds of tons of force, gradually bending the pipe through the desired angle. Even with pipes this size, the bend radius, angle, and final dimensions can be controlled to surprisingly tight tolerances. These bent pipes end up in industrial piping systems, structural applications, and even shipbuilding. We're watching the cutting of a heavy railroad rail, 47 kilograms per meter, which translates to roughly 95 pounds per yard, using oxy-fuel cutting with propane. The oxy-propane torch system operates on a principle that's elegantly simple, yet demands real skill to execute properly. The propane flame, mixed with oxygen in the torch's preheat nozzles, heats a spot on the steel to ignition temperature, around 1600 degrees Fahrenheit for steel. Once that critical temperature is reached, a stream of pure oxygen under high pressure is introduced through the cutting nozzle. Here's the beautiful part. The oxygen doesn't melt the steel, it actually oxidizes it. The steel burns in the oxygen stream, and the force of that oxygen jet blows the molten iron oxide out of the cut, creating the kerf. The operator maintains a specific distance from the workpiece, the gap between the torch tip and the work surface, typically around 1/8 to 1/4 inch. Too close, and the tip will clog with splatter. Too far, and the cut becomes ragged. For cutting rail, you'll notice the torch follows the rail's profile. The rail has this characteristic mushroom shape: wide base, narrow web, and heavy head on top. Each section has different thickness, so cutting speed must be adjusted accordingly. We're now entering the realm of precision machining, where tolerances are measured in 10,000ths of an inch, and programming is just as critical as the actual technique. What you're witnessing is CNC milling of optical chuck jaws, programmed using CAM software, and this represents the perfect marriage of computer manufacturing and skilled craftsmanship. The process begins in the CAM software. A programmer working from engineering drawings creates a three-dimensional model of the chuck jaw, then generates the tool paths that will machine it. The program calculates optimal cutting strategies, selecting appropriate tools, determining feed rates and spindle speeds, and simulating the entire process virtually to catch any potential collisions or errors before a single chip is cut. Watch the CNC mill executing these programmed tool paths. This is likely a high-precision vertical machining center, equipped with a spindle that can rotate at 10,000 RPM or more while maintaining accuracy. Instead of plunging straight down, the tool follows spiral and trochoidal paths that maintain constant chip load and reduce tool wear. Notice the surface finish developing on the chuck jaw faces. These are critical contact surfaces that will grip workpieces, and they must be flat within microns and properly finished to avoid damaging delicate components. The float glass process you're watching, one of those manufacturing breakthroughs that completely transformed the industry. And remarkably, the core principle hasn't changed since it was invented back in the 1950s. Here's how this incredible process works. Molten glass, heated to around 2000 degrees Fahrenheit, flows continuously from the furnace onto the surface of a molten tin bath. The glass literally floats on the tin, spreading under gravity and surface tension, forming a ribbon with parallel surfaces and uniform thickness. Watch as the glass ribbon advances through the tin bath. Temperature is carefully controlled, gradually cooling as the glass moves forward. This controlled cooling, called annealing, is critical. It relieves internal stresses that would otherwise cause the glass to crack or shatter during cutting or installation. As the glass exits the tin bath, it's cool enough to be supported by rollers entering what's called a layer, a long cooling tunnel where temperature continues to drop under precise control. The glass emerges at room temperature, perfectly flat with optical clarity that would have been impossible to achieve consistently using the old methods of sheet glass production. The production line can create thousands of square feet of glass daily, all with consistent quality. The ribbon is then cut to size, inspected, and prepared for further processing like tempering or coating.
What if I told you the world's toughest roads and roofs aren't born on the construction site, but deep inside oil's blazing heart? A material that survives 360-degree heat and brutal cold. One mistake by the technologist, it turns to stone. But why did this black, sticky residue at the bottom of the oil column become the backbone of bridges, airfields, and massive warehouses? And what chemical secret lets it survive for decades without cracking under 40-ton trucks? Every year, the world produces hundreds of millions of tons of bitumen. It's extracted at temperatures between 930 and 1200 degrees Fahrenheit, squeezing literally the last drops from crude oil. Roofing felt? It passes through vats of molten bitumen at 570 degrees, where every inch of cardboard or fiberglass gets soaked in black gold. One wrong step in the process, and within a couple winters, that road's covered in ruts and potholes. Stick around till the end. You'll discover what even some manufacturers won't tell you.
Picture a massive oil refinery. Giant distillation towers, tall as a 20-story building. Crude oil flows in and gets heated to 650 to 750 degrees Fahrenheit. Fractional distillation begins. Light fractions, gasoline, kerosene, vaporize and rise upward. Middle fractions, diesel, fuel oil, remain in the center. And at the bottom of the tower, a heavy tail accumulates, thick, dark residue. This isn't bitumen yet, but it's already the base for it. This residue goes to a vacuum column. There, it's heated again, but under vacuum at reduced pressure. This allows even more fractions to evaporate, which become lubricating oils and paraffins, without pushing the temperature high enough to break down the heavy molecules. What remains after this squeezing out of the heaviest parts, that's the foundation for bitumen and tars. But it's still a raw product. Next, chemistry kicks in. Into enormous reactors, they load this residue and add other components. For example, light oils, polymers, modifiers, sometimes sulfur.
At temperatures between 500 and 650 degrees, the mixture is held so large organic molecules partially cross-link, becoming more viscous and heat-resistant. Complex chemical reactions occur: oxidation, polymerization, condensation. Hydrocarbon molecules unite into even larger and heavier structures.
The result is a thick, extremely sticky material that becomes solid or glass-like when cooled. It can be crushed into chunks, dissolved in organic solvents, or heated to a liquid state and applied as a waterproofing layer. Bitumen is a close cousin of tar, but with a clear focus on road construction and roofing. It's also derived from heavy petroleum residues after vacuum distillation. In large bitumen plants, it's less about pure chemistry and more about fine-tuning viscosity and temperature behavior. If the bitumen is too hard, it'll crack in winter. If it's too soft, it'll run in the heat at 200 degrees on the asphalt.
That's why the technology has a concept called penetration, how deep a needle enters a sample at a given temperature and load. Engineers tweak the ratio of light and heavy fractions, add polymer modifiers to get a material that won't flow in the heat and won't turn brittle in the cold. In massive mixers, bitumen is heated to temperatures from 450 to 650 degrees Fahrenheit, and under intense mixing, they add modifiers, mineral powder, sometimes acidic or alkaline additives to stabilize the structure. That's how polymer-modified bitumens are born, for high-performance roads, airfields, bridge expansion joints. When people say asphalt road, they actually mean a mix of mineral materials, crushed stone, sand, mineral powder, with bitumen as the binder. In huge asphalt mixers, the crushed stone is pre-dried and heated to temperatures close to 570 degrees Fahrenheit to ensure there's no moisture.
Then hot bitumen gets added and mixed until every single pebble is coated in a thin film of binder. The hot mix heads into dump trucks, then straight to the job site for paving. Get the bitumen wrong? A few seasons later, you're looking at ruts, cracks, and potholes. Nail the process? That pavement will handle years of trucks weighing dozens of tons. Roofing felt. It's the story of turning a simple roll of backing into a durable shield against rain, UV rays, and temperature swings. The base is cardboard, fiberglass cloth, or a polyester mesh in roll form, roughly 3 feet wide. Cardboard backing gets picked for budget materials and light-duty jobs, fiberglass when you need better heat resistance and less warping, and polyester for flexible roofs where stretch and tear resistance matter. All these backings share one trait: they're porous, so without treatment they soak up water easily and fall apart fast.
To turn a bare base into waterproofing material, the roll gets run through a processing line with vats of hot bitumen or bitumen resin compounds. The liquid bitumen is heated to a range of 450 to 570 degrees Fahrenheit, sometimes higher, to lower viscosity and ensure quality penetration into the fibers. The roll is fed on rollers into the vat so that it's completely submerged in the melt and passes through at a controlled speed. During this time, bitumen fills the pores of the cardboard or fabric, displaces air and moisture, forming something like a skeleton flooded with waterproof mass. After exiting the vat, excess material is removed by calibrating rollers. This helps maintain the specified thickness and avoid drips. Next comes the stage of forming the coating layers. The saturated base passes under bitumen or resin applicators that apply the main layer on the bottom and top. For this, knife or roller coaters are used. A thin gap between the roller and support measures out the coating thickness.
The bottom layer handles adhesion to the roof deck or foundation, so it can contain more elastic plasticizers, polymers, oils, special additives that reduce the risk of cracking during bending and temperature swings. The top layer acts as armor against sun, rain, hail, and physical damage, so it's made harder and more heat resistant, sometimes modified with polymers for better UV resistance. While the top layer is still hot and sticky, it gets coated with mineral granules.
A dispenser on the line drops a steady stream of mica, basalt granules, or slate onto the moving belt. The particles instantly press into the soft bitumen and lock in place as it cools. This coating isn't just for nice rough texture, it works as a shield against ultraviolet radiation. The sun heats the exposed bitumen surface less, the material ages slower and doesn't crack as fast. Plus, the granules boost abrasion resistance.
After the granules are applied, the sheet moves through a cooling zone. This uses either air cooling or systems with water baths and chilled rollers that pull heat away from the hot bitumen. It's crucial that the temperature drops to a safe level before winding into rolls. If you roll up hot material, the layers stick together, the geometry gets thrown off, and the granules can lose adhesion. To monitor parameters on the line, they install temperature sensors and thickness gauges that ensure the coating layer doesn't come out too thin or too thick. A thin layer means future leaks. Too thick means wasted bitumen and problems during rolling and installation. The next stage is cutting and winding. The roofing felt sheet is cut lengthwise or crosswise into standard rolls, most often between 30 and 50 feet long. Each roll is tightly wound onto a core, so the edges don't shift and the upper layers don't slip. Sometimes one side is left with a strip without granules, covered with pure bitumen.
When laying, this strip gets overlapped by the adjacent sheet, forming a watertight seam that film or granules won't stop you from heating with a torch. Polyethylene or paper liners get added to the roll so the layers don't stick together during shipping and storage. The finished material gets labeled. The tag shows the type of base, the weight of bitumen per square yard, the type of surfacing, the flexibility temperature, and other specs that matter to designers and installers. The story doesn't end there though, because how roofing felt behaves on a roof depends heavily on what exactly got mixed into it back at the factory. If you take regular oxidized bitumen, the material will be cheap but sensitive to temperature swings. On a sunny roof, where the surface easily heats up to 360 degrees in summer, that layer gradually loses elasticity, becomes hard and brittle. To prevent that, polymers get added to the binder. Polymer modifiers make the material more flexible in cold weather and better at handling high heat. Roll roofing can easily withstand both winter freezes and summer scorching without developing a spiderweb of cracks. It's polymer modifiers that gave Roofu Felt new life in the competition with membrane roofing systems. Picture a warehouse complex roof spanning several 100,000 square feet. The classic setup: leveled substrate, a layer of primer from bitumen emulsion, then several layers of roll material with a 4-inch overlap. The bottom layer is often torch applied. You flip it granule side up, heat it with a gas torch until the bitumen softens, and roll it onto the substrate. The top layer goes down the same way, forming a continuous blanket, where the seams are the most critical zones. The quality of that seam determines whether the roof leaks or not. And so, traveling from the bottom of an oil column, through vacuum distillation, through heating to 1200 degrees and oxidation, through vats of molten bitumen at 570 degrees, through coating with mineral granules and cooling, a material is born that protects millions of buildings from rain and snow, withstands 356 degrees of heat and minus 22 degrees of cold, serving for decades without a single crack.
Picture a chunk of metal weighing 130 tons, the size of a 3-story building, spinning at 100 revolutions per minute. This is a supertanker's propeller, the most powerful driving force ever created by humans. Every second, this propeller pushes 200,000 tons of cargo forward. A single sweep of its blade generates the power of 50 cars. But here's the most incredible part. This giant is cast as a single monolith. No welding, no bolts. One solid piece of bronze or steel. How did humanity learn to cast metal structures the size of a house? You'll discover why a propeller like this takes 2 weeks to cool, how it's machined for 3 weeks, and why the tiniest crack could send a ship to the bottom. Watch until the end. The finale reveals the scale of engineering madness that moves the oceans. This is the story of how titans of the seas are born.
The history of the propeller began in the early 19th century. Before that, ships moved either under sail, by oars, or using paddle wheels. Paddle wheels were inefficient. Half the energy was wasted. In 1836, British farmer and inventor Francis Pettit Smith patented the screw propeller. The idea was simple. Rotating blades screw into the water like a corkscrew into a cork, pushing the ship forward. Early propellers were small, 4 to 5 feet in diameter, made from wood or cast iron. But as ships grew larger, so did the propellers. By the early 20th century, steel steamships over 300 feet long appeared. They required propellers 10 to 13 feet in diameter. And with the arrival of supertankers and container ships in the mid-20th century, propeller sizes reached incredible proportions. Modern ocean giants stretching 1,300 feet need propellers 26 to 33 feet in diameter. That's the height of a 3-story building.
The world's largest propeller was built for the Emma Maersk container ship, one of the biggest vessels on the planet. The propeller's diameter? 31.5 feet. Weight? 131 tons. That's 2 tanks combined, or 17 elephants. The propeller has 6 blades, each the size of a car. Total blade surface area? About 750 square feet, like a big apartment. The ship's engine produces 109,000 horsepower. All that power flows through a single propeller. At full speed, the blade tips slice through water at 125 miles per hour. Water pressure on the blades? Dozens of tons per square foot. Any crack, any casting flaw, and centrifugal force rips the propeller apart. The ship's dead in the middle of the ocean. That's why manufacturing these propellers is the pinnacle of metallurgy and engineering. The slightest mistake is unacceptable.
Where and how do they make these monsters? The largest propeller manufacturers are in Japan, South Korea, China, Germany, and the Netherlands. The most famous include Japan's Nakashima, Germany's Mecklenburg Metallgas, and the Dutch Works4. They have foundries the size of a football field and cranes that can lift 200 tons. The process starts with design. Engineers calculate blade shapes on supercomputers. Angle of attack, curvature, thickness, everything affects efficiency. The propeller needs to create maximum thrust with minimal cavitation, the formation of water bubbles that destroy metal. The tiniest miscalculation and the propeller becomes inefficient or wears out fast. After the calculations, they create a full-size wooden model of the propeller. Yes, wood, 31 feet in diameter. Master craftsmen carve it for weeks using blueprints and templates, precision down to a millimeter. This wooden model becomes the foundation for creating the casting mold.
They coat the wooden pattern with a special compound and place it in a massive flask, a steel box the size of a room. Around the pattern, they pack in molding sand, sand mixed with binding agents. The mixture gets packed layer by layer. Each layer is compacted through vibration and pressure. The process takes several days. Once the flask is full, they split the mold into 2 halves and carefully remove the wooden pattern. What remains is a cavity shaped like the propeller, a negative.
They coat the interior surface of the mold with a refractory compound, so the molten metal won't damage the sand. Then they bolt both halves back together. The mold has to withstand the pressure of 130 tons of liquid metal. They install the gating system, channels that'll feed metal into the mold. It's calculated so the fill happens evenly, without air pockets or cold joints. The mold is ready. Now comes the really impressive part, melting the metal. In the foundry, there's a massive induction furnace, a steel crucible holding 40 cubic meters wrapped in electromagnetic coils. They load it with bronze or alloyed steel stock, bars, ingots, scrap. 140 tons of metal. That's with a buffer. Some will stay in the gates and risers. They flip the switch. Powerful electromagnets induce eddy currents in the metal. The metal starts heating from the inside. Temperature climbs to 1600 degrees Celsius. The metal melts, glows orange, then white. The surface churns. The crew skims off slag, oxides and impurities floating to the top. They add alloying elements, manganese, nickel, aluminum, for strength and corrosion resistance. They pull a sample of the melt, analyze the composition. When everything's ready, they start the pour. The furnace tilts with a special mechanism. Molten metal flows into a massive ladle suspended from an overhead crane. The ladle holds 140 tons. This is the most critical operation. The metal has to be uniform in composition and temperature.
The crane moves the ladle toward the mold. The metal glows a blinding white, so bright you can't look at it without dark glasses. The temperature around it climbs to 140 degrees, even though the ladle's 30 feet away. Workers in silvery heat-resistant suits control the pour. They open the ladle gate. Molten metal flows into the gating system. First as a thin stream to preheat the channels. Then the flow gets stronger. The metal fills the mold from bottom to top, pushing air out through special ventilation channels. The pouring process takes about an hour. 300,000 pounds of liquid metal transfer from ladle to mold. When the mold is full, they close the ladle gate. The metal surface in the mold forms a crust of oxides. They dust it with a special powder that creates a protective layer. Now the waiting begins. The metal has to cool and solidify. But at this size, that's not quick. 260,000 pounds of bronze or steel cool slowly, very slowly.
Two weeks, 14 days the mold sits untouched. Inside, crystallization slowly occurs. Molten metal transforms into solid. Temperature drops at a rate of a few degrees per hour. Cooling too fast leads to cracks from uneven shrinkage. Too slow, large metal grains form, reducing strength. Engineers monitor the process with thermocouples, temperature sensors embedded in the mold. After 2 weeks, they break open the mold. A crane lifts the flask, opens it up. The molding sand pours away, revealing the casting. Before their eyes, a giant propeller, covered in black scale. Weighs 150 tons, 20 tons more than the finished product. Excess metal has solidified in the gates, risers, and allowances. The propeller moves to a special stand. Machining begins, transforming the rough casting into a perfect ship's propeller. And that's another 3 weeks of work. First, they cut off the sprues and risers, solidified metal feed channels. They use gas torches and heavy-duty bandsaws. The cut-off chunks weigh several tons each. They'll go back to the melt shop too. Then rough machining begins on turning and milling machines. These are giant machines, a bed 20 meters long, a milling head weighing 10 tons. The propeller is clamped on a rotating table. Cutters remove the stock, excess metal left for machining. Chips fly off in spirals as thick as a finger. Tons of metal are removed per shift. They mill the hub, the central part of the propeller that fits onto the shaft. A hole about 3 to 5 feet in diameter has to be perfectly round and concentric, precision tenths of a millimeter. Then they machine the blades. Each blade is milled to a complex profile, leading edge, trailing edge, face, back. The profile changes from root to tip. It's a three-dimensional, doubly curved surface. The machine runs on computer control from a program based on design data. After roughing comes finishing. Fine-toothed cutters pass over the blade surfaces, removing fractions of a millimeter. The surface becomes smooth. Then polishing. Abrasive wheels buff the blades to a shine. This is critically important. Surface roughness increases water resistance and promotes cavitation. A perfect surface cuts a ship's fuel consumption by percentage points. For a supertanker, that's millions of dollars in savings per year. After machining, the propeller is weighed and balanced. The center of mass must lie exactly on the rotation axis. Otherwise, vibrations will develop during operation, destroying bearings and potentially damaging the ship's hull. Balancing is done by drilling small cavities in specific locations. The final operation, non-destructive testing. The propeller is X-rayed, checked with ultrasound, examined using magnetic particle inspection. They're looking for internal defects, voids, cracks, inclusions. If they find a critical defect, the propeller is scrapped. 287,000 pounds of metal and a month of work go to waste. The cost of such a propeller, $1 to $3 million. And just like that, making the journey from a wooden model through the hellish heat of 1600 degrees and 140 tons of molten metal, through 2 weeks of cooling and 3 weeks of machining on giant lathes, a propeller is born, the heart of a supertanker, the pulse of an ocean giant. A solid piece of metal the size of a house, weighing 130 tons, capable of transmitting 100,000 horsepower. It's a triumph of engineering brilliance and metallurgical mastery. Every time you spot a container ship on the horizon or an oil tanker in port, know this: beneath the water spins a titan, born in fire and honed to perfection. A monolith of bronze or steel, every square inch of which withstands tons of pressure. A propeller that drives forward half the world's trade. 90% of all cargo moves by sea. This is a story about giants created by humans, about how humanity learned to cast metal the size of a house and machine it with precision down to a millimeter. A propeller isn't just a chunk of metal. It's a symbol of man's dominion over the oceans, a symbol of the technology that connected continents. From wooden model to steel reality, a journey spanning 5 weeks and millions of dollars. A journey repeated hundreds of times a year in foundries across the world, so the planet's fleet keeps pushing forward.
A poisonous metal that saves lives. Sounds paradoxical, but it's true. Lead, one of the most toxic elements on Earth. It poisoned Roman emperors, killed thousands of workers, got banned from paint and gasoline. But without it, not a single car on the planet would start. Every second, the world produces 2 tons of lead. 85% goes into batteries, the heart of every vehicle. Lead shields doctors from X-rays and stops radiation at nuclear plants. The heaviest common metal you can hold in your hands, 11 grams per cubic centimeter. How do you get a bluish metal that kills and saves at the same time from silver ore? You'll find out why the Roman Empire fell because of lead pipes, how a lead-acid battery works, and why this ancient poison is still irreplaceable today. Watch till the end. The finale reveals the dark side of progress. This is the story of a metal humanity can neither embrace nor let go. Lead's story begins deep in ancient times. About 7,000 years ago, people learned to smelt lead from ore. It was one of the first metals humans extracted from stone. Lead melts at a low temperature, just 627 degrees Fahrenheit. Even a campfire can melt lead ore. The ancient Egyptians used lead to make statuettes and cosmetics. Yes, women lined their eyes with lead-based white paint. The Roman Empire took lead use to absurd levels. Lead water pipes stretched throughout Rome. Wine was stored in lead amphorae. The metal made the drink sweeter. Wealthy Romans ate from lead dishes. Aristocracy sweetened wine with lead sugar, lead acetate, which actually tastes sweet. The result? Mass poisonings. Roman nobility suffered from gout, insanity, infertility. Many historians believe lead poisoning of the elite became one of the causes of Rome's fall. Emperor Nero, known for his madness, may have been poisoned by lead since childhood. In the Middle Ages, lead was used to make cathedral roofs, stained glass windows, and printing type. Alchemists considered lead the basest of metals and tried to turn it into gold. The 19th century brought a boom in the lead industry. Lead white became the foundation for paints, bright, durable, cheap. Lead coated toys, furniture, house walls. Children gnawed on lead toys and died from poisoning. Workers at lead plants perished by the dozens. Metal dust destroyed their nervous systems. In the 20th century, lead was added to gasoline as an anti-knock additive. Tetraethyl lead boosted octane ratings. Engines ran smoother. But exhaust fumes poisoned cities. By century's end, leaded gasoline was banned almost everywhere. Lead paints were banned too. Lead pipes replaced with plastic. It seemed the age of lead was over. But no, lead production kept growing because a new massive application emerged: car batteries.
Where does lead come from today? The primary lead mineral is galena, lead sulfide, cube-shaped crystals, silvery gray with a metallic luster, extremely heavy, density of about 0.27 pounds per cubic inch. Galena often occurs alongside silver, zinc, copper. The largest deposits are found in China, Australia, the USA, Peru, Mexico. China produces half the world's lead, around 6 million tons per year. Lead is extracted through open-pit mining in quarries or underground mines. They blast the rock, crush it, grind it. The result is ore containing 3 to 10% lead. That's enough for industrial processing. The ore is enriched through flotation. Crushed ore is mixed with water and special reagents. Galena particles stick to air bubbles and float up, forming foam. Waste rock gets washed away. The concentrate contains up to 70.
Lead concentrate gets roasted in massive furnaces at around 1800 degrees Fahrenheit. Lead sulfide transforms into lead oxide, releasing sulfur dioxide gas. They capture this gas and use it to make sulfuric acid. Nothing goes to waste. Lead oxide gets mixed with coke and fluxes, limestone or quartz. Loaded into a shaft furnace. Hot air blasts in from below. Temperature climbs to 2200 degrees. Carbon reduces the lead oxide back to metal. Molten lead pools at the bottom of the furnace, a heavy gray-blue liquid. Lead is 11 times denser than water. Drop a steel ball into molten lead and it'll float right on the surface. They tap the melt from the furnace into ladles. The melt's still impure, contains copper, zinc, silver, gold. Yeah, lead ore often carries precious metals. Extracting them pays for part of production. Lead gets refined, purified. Heat it to 900 degrees and add zinc. Silver and gold dissolve in the zinc and float up. They skim them off. The purified lead gets poured into ingots. A standard ingot weighs about 55 pounds and is the size of a brick, but it weighs like a bag of cement. Try lifting it. Lead is heavy and soft. You can cut it with a knife, scratch it with your fingernail. At room temperature, lead develops a dull oxide film, loses its shine. A fresh cut is silvery blue, beautiful, but goes dull within a minute. Lead doesn't rust in the usual sense. The oxide film protects the metal from further corrosion. That's why Roman lead pipes have survived 2,000 years. But the key property of lead is its toxicity. Lead and its compounds are poisonous. Once it enters the body, lead accumulates in bones, replacing calcium. It destroys the nervous system, causes anemia, damages kidneys and brain. Especially dangerous for children. Even tiny doses disrupt nervous system development. There is no safe level of lead in blood. Any amount is harmful. That's why working with lead demands the strictest safety measures: respirators, protective clothing, showers after every shift.
But if lead is so toxic, why do they keep producing it in such massive quantities? Because lead has properties that simply can't be replaced. First, its weight. Lead is 1.5 times heavier than iron. Second, it's soft and easy to work with. Third, it blocks radiation. Gamma rays and X-rays are absorbed by lead better than any other affordable metal. Only gold and tungsten are better, but they're way too expensive. So lead gets used for radiation protection. X-ray room walls are lined with lead sheets. Doctors and technicians wear lead aprons, weigh about 10 pounds, uncomfortable, but they protect. Containers for transporting radioactive materials are made from lead several inches thick. At nuclear power plants, lead is used in shielding systems. Viewing windows for observing reactors are made from leaded glass, transparent, but contains up to 70% lead oxide. This glass stops radiation while letting light through. Without lead, nuclear medicine and power wouldn't be possible.
But the main use of lead? Batteries. 85% of global lead production goes into lead-acid batteries. These are the most common type of battery on the planet. Every car with an internal combustion engine has one. 1 billion cars means 1 billion lead batteries. How does it work? Inside a plastic case, there are plates made of lead and lead dioxide submerged in sulfuric acid. During discharge, the lead and lead dioxide react with the acid, forming lead sulfate and water. Electrical energy is released. During charging, the process reverses. Electricity converts the lead sulfate back into metal and dioxide. This cycle can repeat hundreds of times. Lead-acid batteries are reliable, cheap, and can handle high currents. Perfect for starting an engine. A starter motor draws hundreds of amps. Lithium-ion batteries can't compete in this application yet. One car battery contains between 22 and 33 pounds of lead. It lasts 3 to 5 years, then gets recycled. Lead is the recycling champion among all materials. Up to 99% of lead from old batteries makes it back into production. An old battery gets dropped off at a collection point where it's disassembled and crushed. Lead plates are melted down, purified, and cast into ingots. A new battery contains up to 80% recycled lead. This makes economic sense. Secondary lead costs less than primary. And it's environmentally sound. No need to dig new mines. Global lead production runs about 12 million tons per year. Roughly half comes from recycled material. Lead prices hover around $2,000 per ton, cheap compared to other metals. Beyond batteries and radiation shielding, lead shows up in cable sheathing, ammunition, fishing weights, and wheel balancing weights, in construction for soundproofing and waterproofing. But these uses are gradually declining as manufacturers hunt for less toxic alternatives. Lead's future lies in batteries and radiation protection. Until someone invents a replacement, lead remains irreplaceable.
And just like that,
traveling from silvery galena crystals through the inferno of furnaces at 1200 degrees and complex purification from impurities, lead emerges, the most contradictory metal in human history, a metal that poisoned Roman emperors and saves lives in hospitals. Banned in paints and toys, yet no car starts without it. Heavy, soft, toxic, but irreplaceable. This is the story of progress's dark side, how a poisonous element became the foundation of modern civilization. Every time you turn your ignition key, get an X-ray, or have a chest scan, know this: lead is working for you, shielding you from radiation, storing energy, starting engines. The paradox of a metal that kills when mishandled and saves when used right. 7,000 years alongside humanity, from ancient figurines to modern batteries. Lead is a reminder that progress always has a price, and that price is sometimes written on the periodic table with the symbol Pb, plumbum, from the Latin word meaning heaviness, the weight of choosing between toxicity and necessity. A metal humanity cannot abandon, no matter how hard it tries.
Imagine a gas capable of changing the course of history. It can disinfect water, create plastic without which modern life is unthinkable, and at the same time become a deadly weapon. This is chlorine. Annually in the United States, over 12 million tons are produced, as much as 120 Gerald Ford aircraft carriers weigh. But the real mystery isn't in the numbers. It's hidden in the technology itself. How does simple salt water, with the help of electricity, give birth to 3 products that support entire industries? Watch carefully. At the end of this video, you'll learn a fact that will forever change your understanding of this invisible foundation of modern civilization. The United States is one of the world's largest producers of chlorine. Annually, factories in the country produce over 12 million tons of this gas. This figure simply doesn't fit in one's head. Imagine the weight of the Gerald Ford aircraft carrier, the world's heaviest military vessel. That's about 100,000 tons. This means that in 1 year, American industry produces as much chlorine as 120 such carriers weigh. Everything begins not in a laboratory, but deep underground. The main ingredient for our recipe is ordinary rock salt, or sodium chloride. It's either mined in mines or, much more efficiently, pumped from underground. Water is pumped into deep underground salt deposits. The water dissolves the salt, forming a saturated saline solution called brine. And it's precisely this concentrated salty solution that's our raw material. But it's still dirty. It's full of impurities, calcium, magnesium, and other minerals. Therefore, before the main show begins, the brine undergoes thorough purification. It's passed through an entire series of tanks where, with the help of chemicals, all impurities are precipitated and filtered from it. At the output, we obtain a perfectly clean, transparent, and very salty solution, ready for the main event, electrolysis. These are electrolyzers, or cells. It's precisely here that all the magic will occur, or more accurately, all the chemistry. Let's imagine one such electrolyzer. Essentially, it's a box into which our pure saline solution is poured. And into this solution are immersed 2 electrodes, a positively charged anode and a negatively charged cathode. Now to these electrodes is applied a direct electrical current of colossal force. And here the breakdown begins. The salt molecule in water breaks down into positively charged sodium ions and negatively charged chlorine ions, and the electrical field forces them to move. The positive sodium ions, like a magnet, are attracted to the negative cathode, and the negative chlorine ions to the positive anode. Two such chlorine atoms, having lost their charge, immediately unite, forming a molecule of gaseous chlorine. Billions of these molecules gather together and on the anode surface begin to appear tiny bubbles of greenish-yellow gas. This is our chlorine. The main resource for chlorine production is electrical energy. The chlor-alkali industry is one of the largest consumers of electrical energy in the United States. To produce 1 ton of chlorine requires approximately 2,500 kilowatt-hours of electricity. Now, let's multiply this by 12 million tons per year. It turns out that this industry annually consumes about 30 billion kilowatt-hours. That's more than the annual electricity consumption of entire states such as Vermont or Wyoming. But they don't transform into metallic sodium. Instead, electrical current splits the water molecules present in the solution into hydrogen and hydroxide ions. At the cathode are released bubbles of pure hydrogen. This is our first byproduct. And the hydroxide ions remaining in the solution combine with our sodium ions, forming sodium hydroxide, or caustic soda. This is our second incredibly valuable byproduct. But here arises an enormous problem. We've just obtained 3 substances, chlorine, hydrogen, and caustic soda, and they must not be mixed under any circumstances. Chlorine and hydrogen together form an explosive mixture, and chlorine and caustic soda react, forming bleach, which we don't need at all. This membrane, made from special polymer, resembles a bouncer at a nightclub. It allows positive sodium ions through, permitting them to pass to the cathode, but blocks negative chlorine ions, preventing them from entering the cathode space. Thus, chlorine is born and collects in one part of the cell, whilst hydrogen and caustic soda collect in another. Now we need to gather our harvest. From the anode chamber is continuously pumped wet, hot, greenish-yellow gas. First it must be cooled, then it must be dried. Chlorine is incredibly aggressive, especially in a wet state. It corrodes almost everything. But there's one substance it doesn't touch: concentrated sulfuric acid. It's compressed under enormous pressure and simultaneously cooled. Under this double assault, the gas transforms into a transparent, amber-yellow liquid resembling oil. This liquid chlorine is far more convenient to transport and store. It's poured into special thick-walled steel tanks or railway wagons. Every step of this process occurs under conditions of absolute seal, because leakage of this gas is deadly dangerous. And what about our byproducts? They're no less important. The hydrogen we obtained is collected, purified, and used either as fuel for the factory itself or sold. And the caustic soda solution that formed is pumped out, concentrated, and sold. And so, from simple salt water, passing through it an enormous quantity of electricity, people have learned to obtain 3 extremely important substances at once, which are the foundation for thousands of other products. Now let's look at where all this enormous quantity of chlorine goes. You might think it all goes to disinfecting swimming pools, but that's merely a drop in the ocean. In reality, less than 5% of all chlorine is used for water disinfection. And where does the remaining 95% go? It's a key building block for other products. About 40% of all chlorine goes to producing this universal plastic. Vinyl windows in your house, water pipes, medical drips, the credit card in your wallet, all of this was born thanks to chlorine. Another 40% approximately is used for creating thousands of other organic and inorganic compounds. Pharmaceuticals, solvents, refrigerants, herbicides, insecticides, the list is endless. And chlorine is also a key component for bleaching paper, giving it that very clean white color. And finally, about the byproducts, which are actually no less important. We remember that for every ton of chlorine, we obtain approximately 1,100 kilograms of caustic soda. This means that annually, American industry produces over 13 million tons of this important alkali. This makes chlor-alkali production a perfectly balanced business.
Inside, the pressure hits 2,300 pounds per square inch. Temperature, 608 degrees Fahrenheit. Wall thickness, 8 inches of solid steel. This is a nuclear reactor vessel, one of the most complex industrial objects humans have ever built. It weighs 330 tons, stands 36 feet tall. Diameter, more than 15 feet. Service life, 60 years of continuous operation under radiation bombardment. Inside, a controlled chain reaction unfolds. Billions of uranium atoms splitting every single second. And it's all contained by one steel shell that can't develop even the slightest